to assess human requirements for carbohydrate as part of a new review of DRIs for macronutrients, which is indicated on the project website. Purpose of today's open meeting is to hear from the experts who will provide overviews of the evidence on human requirements for carbohydrate. I want to note that this is an open on the record session. Interested individuals and members of the press have been invited to attend as observers. We will not entertain questions from the floor, only from the sponsors and the committee. I would also like to remind everyone that this is an information gathering session. That is, the committee is in the process of assembling materials that it will examine to discuss the course of making its findings, conclusions, and recommendations. Therefore, I ask everyone here today to be extremely mindful of the fact that the committee has made no conclusions and that it would be a mistake for anyone to leave here today thinking otherwise. Comments made by individuals, including members of the committee, should not be interpreted as positions of the committee or of the academies. In addition, committee members typically ask probing questions. We hope they will be probing questions in information gathering sessions that may not be indicative of their personal views. So before I share some introductory slides, I'd like to call on members of the standing committee to briefly introduce themselves. First, Dr. Atkinson.
Good morning, everybody. Stephanie Atkinson. I'm professor of pediatrics at McMaster University in Hamilton in Canada.
Thank you. Dr. Das.
Good morning. I'm a senior scientist at the John Mayer USDA Human Nutrition Research Center on Aging and a professor at the Friedman School of Nutrition at Tufts, all in Boston. Thank you.
Thank you. Dr. Herring. Let's see if I see her here. I do not see her yet. Dr. Krebs couldn't make it today, class conflict. Dr. Lichtenstein.
Hi, Alice Lichtenstein from the Jean Mayer USDA Human Nutrition Research Center on Aging at Tufts University. I'm director of the Cardiovascular Nutrition Laboratory and also the Gershoff Professor of Nutrition Science and Policy at the Friedman School, everything at Tufts University.
Thank you. Valerie, I saw you before. There you are.
I'm Valerie Tarasek. I'm a professor in nutritional sciences at the University of Toronto.
Thank you. I think Dr. Van Horn was going to be on the call on phone. Dr. Van Horn, are you on? I don't think so. Not yet. So it should be on later. And Dr. Yetley.
Beth Yetley, retired nutrition scientist from NIH.
Thank you very much. Now I'd like to ask Krista Eslinger to make some opening remarks on behalf of the sponsor.
Thanks, everyone. I'm Krista Eslinger with the Office of Nutrition Policy of Promotion at Health Canada, and I'm the chair of the Joint Federal Working Group. I'd like to thank you all so much for giving your time to be here today. And I'd like to say that although Health Canada is the sponsor of this particular session, really that's in its capacity as a member of the Joint Federal Working Group on DRIs, which includes members from many other US federal government agencies as well. So really it's on behalf of the whole working group that I'm going to give some opening remarks, and I'll try and set a little bit of context for why we're having this meeting. I think everybody here is well aware that the DRIs are a really important foundation to nutrition policies and programs, and that because of this, it's important that they be kept up to date as new and relevant evidence becomes available. And the macronutrients, which include protein, fat, carbohydrate, and their subcomponents, are among the most relevant current concerns in nutrition, but the existing DRI values were published 20 years ago. And since then, there's been a lot of evolution, both in the science on nutrient health relationships and in the DRI process itself and how evidence is organized and used. because of their importance to many different policies, the Joint Federal Working Group has launched an effort to update all the DRI values for macronutrients in the coming years. And we're in the process right now of preparing the evidence reviews that will be needed to help support the revisions to the DRI values. As you know, there's different types of DRI values that can be established for any given nutrient. There's values for nutrient adequacy, values for prevention of adverse effects, and values relative to chronic disease risk reduction. And importantly, there's different types of evidence that underpin the different types of values. And identifying the appropriate endpoints and outcomes for each type of reference value is really fundamental to their derivation. And an important input to establishing DRI values are objective, systematic reviews of the evidence that's available on a nutrient and the potentially relevant outcomes. However, systematic reviews are really resource intensive in terms of time and cost, and particularly in the context of the macronutrient review, where there's so many nutrients to be addressed more or less concurrently. The Joint Federal Working Group needs to be thoughtful about prioritizing where resources are best used in undertaking systematic reviews and where we might be justified in taking another path. Today's topic is human requirements for carbohydrate. And typically, DRI requirement values are based on data relating either to nutrient balance studies, depletion repletion studies, biochemical measures, clinical indicators. But it seems that carbohydrate has very few potential indicators. And the Joint Federal Working Group really wanted to obtain some expert input to help in identifying what data may be out there that could be relevant to establishing requirement values for carbohydrate. We're particularly pleased to be able to have this session take place through the Standing Committee for the Review of Dietary Reference Intakes Framework, because this committee was put in place to address overarching issues related to DRI concepts and to facilitate a consistent approach for reviewing and setting the DRI values. And the expertise that you guys bring on the DRI framework, on the type of evidence that's needed to derive DRI values, the applications of DRI values, is going to be really valuable to the discussions today and really help inform the decisions that the Joint Federal Working Group will have to make. And so with that, we look forward to the presentations and to what's sure to be thoughtful discussion on this intriguing topic. Thank you.
Thanks so much for your introductory remarks. And I apologize to Nadine. I skipped over here on my list. Could you introduce yourself, please?
Yes, that's okay. Good morning, everyone. I'm Nadine Sahyun, and I'm a professor, excuse me, professor in the Department of Nutrition and Food Science at the University of Maryland in College Park. Thanks.
Thanks so much. Apologize again. Can we go to the introductory slides, please? So once again, the focus today is on assessing human requirements for carbohydrate. And we go next slide, please. So here's a slide on workshop goals. The study sponsors are Health Canada and also USDA ARS. And they've asked the Standing Committee to do the following: inform the study sponsors about the best approaches for systematic reviews used to assess human requirements for carbohydrates, as you just heard, to inform the new DRI process for macronutrients. So we will have 4 presentations today and also a follow-up panel discussion that we'll discuss and review evidence on the following: relevant biological roles of dietary carbohydrates, physiological effects of low carbohydrate intake, indicators of carbohydrate adequacy and inadequacy, indicators relevant to subpopulations, including racial, ethnic groups, and maternal and infant populations, and also relevant health conditions prevalent in the population, including obesity and diabetes. Next. Next slide, please. So this is our agenda. Again, I thank the 4 speakers for making time and spending quite a bit of effort to put together their presentations. Each presentation is designed for 20 minutes, and then there's going to be about 15 minutes of Q&A afterwards. and members of the standing committee will moderate the discussion afterwards. And as you can see in the end, there'll be a panel discussion where we'll have a chance to really dial in on the overall questions that have been asked of us. Next, please. So I thought it would be important that everybody's on the same page as to what population we're discussing as far as dietary reference intakes. So as many of you know, since the very first edition of the RDAs in 41, committees have provided some context to the intended population. So you see terms such as healthy populations or apparently healthy populations. There wasn't really very much context around what that really meant. So the sponsors asked the standing committee a question, should there be a different term considered rather than apparently healthy populations, since DRIs were developed to determine recommended intake of nutrients to meet the needs of the majority of the general population, and the health status of this population has shifted. So in our first letter report for the standing committee, in part, we define the term general population. And if you can go to the final introductory slide. So the standing committee provide advice that the general population base should be as wide as possible, and that each DRI committee, in consultation with the standing committee, should establish exceptions to the general population on a nutrient to nutrient basis. So general population may vary from, depending on whether it's macronutrients or folate or B12 or something. Exceptions should be based on evidence that a particular disease, health condition, disability, or medication is likely to alter the requirement for nutrient under review. So this is an effort to have as large a population considered as possible. So thank you. That's the end of my slides. And at this point, we're going to start off with Dr. Beer as our first presenter. Dr. Beer is professor of pediatrics and director of the USDA ARS Children's Nutrition Research Center at Baylor College of Medicine. His research interests include the role of maternal, fetal, and childhood nutrition on growth, development, and adolescent health, and long-term consequences of nutrient inadequacy in early life, particularly the macronutrients, on chronic diseases, outcomes in adulthood. He will be speaking about the physiological basis for the RDA for human homeostasis. Welcome, Denny. You need to unmute yourself.
Well, I thought I did, but I guess I didn't. Anyway, all right, I'm here to talk about physiology. They had to find somebody old enough who was born before omics. So when we had metabolism instead of metabolomics, and it was here before we had PubMed. And what I'm going to talk to you about is why I think carbohydrates are Mother Nature's favorite fuel. Okay, now that should move. Now, doesn't seem to want to go. Well, all right, so I don't know if I did that or it went by itself. All right, yeah, these are the disclosures I've consulted for everybody over a long academic course. So I'm completely conflicted, but I contend that all of these places I've consulted for are competing with each other. So I cancel out any of the potential conflicts in the end. In addition, essentially nothing that I am going to try to quote unquote sell today is less than about 50 years old. And it's well beyond the usual shelf life and pull date of most things that may have a commercial interest. Why that doesn't seem to want to advance. So somebody has, oh wait, there's okay. Now, all right, in a galaxy long ago, but not very far away, and we are here. This is our galaxy, and so it's really not very far away. It all happened here, and the things I'm going to talk about happened before PubMed, when we had Index Medicus, and anybody who's old enough to remember that, I give you thanks. And scientists didn't have artificial intelligence, so they were forced to use the real thing. So we're going to talk about hard data, no models, no constructs, pretty much. And even though these data are old, Otto Warburg said almost 100 years ago that good experiments are right forever. If you do it right the first time, it'll still be right 50 years later. Let's see if I... Okay, so I'm going to make a brief argument that says sugars are Mother Nature's most essential nutrients. So humans can make every sugar they need for life. And this creates a problem when you're talking about requirements, right? Because if you can make everything, do you have any requirements? And this is why I prefer the terms like reference intakes and allowances, because in the strict requirement sense, you, in theory, can make what you need. In addition, irrespective of whatever the mother is eating, the fetus, which one could argue is our principal evolutionary product, obtains all of its energy supply from glucose in the end. And third, the brain, which I think arguably is the highest achievement of evolution, the human brain, okay, prefers to consume only glucose. So even though right at the moment sugars are getting a bad rap, they're getting a bad rap, I would argue that this is a little bit misplaced in the context of their importance to physiology. Now, we've known, I mean, the brain, it's been known that the brain consumes glucose for a very long period of time. And back in the 1940s, that is 80 years ago at least, there were studies in which investigators measured the balance of substrates across the brain. Now, this is one of my favorite studies. First, Erna Gibbs was a woman, and this alone makes this rather exciting in 1942. She published initial studies on the ability of brain blood flow to monitor carbon dioxide and gas concentrations, and she won the Lasker Clinical Award and the Mead Johnson Award in pediatrics, the highest awards that are available. Rather remarkable person. But here's a study that she was the first author on that appeared in the JBC 80 years ago. And just think about this today. So these are 50 males, almost all of the medical students, right? Now you can imagine how they volunteered for this study, right, in medical school, and they were chosen, and they lay quietly, and the internal jugular vein was punctured. Now remember, this is a time when we didn't have micro, machine sharpened, new needles. These were reusable needles. These were all these mega trocar kind of needles that, some of us remember. And the authors say, care was taken to see that the subjects breathed normally during and immediately preceding the taking of the sample. Now, I don't know about you, but, this would have been relatively hard to do, given that someone was going to put, a big needle in my jugular vein. But anyway, here's 50 subjects in which the measured brain arteriovenous RQ was 0.99, unequivocal evidence that essentially all of the fuel of the brain was glucose. Now this brain AVRQ has been measured, I don't know, many times in multiple studies. And under normal circumstance, the brain only burns glucose for energy with a little percent maybe left over. And since that time, there have also, in the context of measuring AV differences of glucose across the brain, we have a huge body of literature. I mean, honestly, I didn't go try to search it all out and make a slide, but, on the whole, the resting adult brain consumes about 5.5 or 5.6 milligrams per 100 grams of brain per minute. And since the adult male brain is about 1,400 grams, this comes out to be about 110 or so grams of glucose a day. Okay. All right, then about 25 years later, all of the, I'm a little bit ahead of myself. Okay, so the brain is consuming, the liver produces about 200 grams of glucose a day. And of that glucose, about 60% goes to the brain and is irreversibly oxidized to CO2. This is the critical thing to remember. It's lost. The glucose carbons are gone. So if one wants to keep up presenting the brain with 100 and something grams of glucose, one has to have new carbons. And these data, by the way, which were collected, in the late 60s and 70s by the people on the bottom, everyone except Errol Morales is now deceased. I mean, these are individuals who wrote the book on what happens if you don't eat, then you starve after an overnight fast, and then you eventually starve, for much longer periods of time. So of the 100 and plus grams of glucose that go to the brain that are lost to the system, gone, period. About 50 grams go to red and white blood cells, and through the Cori cycle are recycled back into glucose. Another 50 grams or so go to muscle, and in muscle, as we'll come to, we have conversion to amino acids, and those are released as gluconeogenic amino acids. And finally, there's a bit of glycerol coming from the adipocyte. I don't know why we can't, okay. Don't know why this isn't working. Okay, so the first thing you need to remember is that you can't make net glucose from oxidation of fatty acids. When fatty acids are oxidized, they become acetyl-CoA, i.e. 2 carbons. And in the process of going through the citric acid Krebs cycle and to oxaloacetate and be made into glucose via the gluconeogenic pathway, okay, 2 carbons are lost from the TCA cycle. So 2 carbons enter from oxidation of fat and 2 carbons leave during the turning of the TCA cycle. So if you put a tracer in the fatty acids like carbon 14 or carbon 13, you'll find some tracer in glucose. But that is not net movement of glucose carbons, because some of those carbons that are lost in the TCA cycle are different, and some of them are the tracer. And in the end, you can't put 2 carbons in, have 2 carbons leave, and make any net glucose. So from fatty acids alone, you can't replace that 100 and something grams of glucose that needs to go to the brain. But you can get some new glucose from the lipolysis of adipose tissue. That is, adipose tissue, well, triglycerides have a backbone, a glycerol backbone. And usually these are a relatively minor contribution. And I would give you a better number, but there's a lot of debate about how one actually measures gluconeogenesis from glycerol. And most people would say it's a small percentage, 5, maybe even 8 or 9% or something in the usual post-absorptive state. And under states of lipolysis, starvation, it may go up even as high as 20 or 30%, but normally it's a relatively minor contribution. You also make ketones from the fatty acids that are delivered to the liver and oxidized in the liver. And we always have ketone bodies circulating in the blood, usually in the low, let's say 100 micromolar range. And ketogenesis feeding the brain only becomes important when ketone body levels are elevated. And, whoops. And I missed the slide I'll come back to. All right, and we actually have data. So here are data that show, using PET, that the cerebral metabolic rate of glucose is inversely proportional to the cerebral metabolic rate of acetoacetate when ketones are infused. So there's, and these data have been repeated in different ways. There's absolutely no question that the brain can consume keto acids if in fact the levels are elevated. Otherwise, they don't represent much of the fuel source of fatty acids of the brain. Now, the most unique study, N of 1 study, 3 adults, 3 obese adults, 2 women, 1 man, fasted for 40 days, appeared in 1967 from Ollie Owen's group. And this study showed absolutely conclusively by measuring fuel balance and across the brain, that on the right-hand bar, you can see that after 40 days of starvation, acetoacetate and beta-hydroxybutyrate represented about 60% of the fuel source of the brains of those 3 individuals. Now, you also need to know that the total amount of fuel oxidized, that is the fuel, rate, decreased substantially over 40 days of fasting. So this is 60% of a lower number than existed in the fed state. But the other thing you need to know in this study is that circulating acetoacetate and beta-hydroxybutyrate concentrations were over 7 millimolar. Now, if you fast overnight, you get to maybe 1 millimolar. If you do a ketogenic diet, maybe you can get to 3, but most of the time it's 1.5 or so millimolar. So this is a circumstance that's beyond most of the kinds of things that we run to in everyday life. So here's one slide I skipped over somehow in my inability to make them turn. Okay, so the other thing you need to know is that if you make glucose by recycling lactate and pyruvate, as I showed in the prior slide, that were originally derived from glucose themselves, okay, you don't make new glucose. Even though these carbons go through the gluconeogenic pathway, you make old glucose. So somebody, I wish it were me, 50 years ago, made the term gluco-oldogenesis. So you get new glucose carbons when that happens. So you can't make new glucose carbons for the brain by recycling lactate and pyruvate. If you make lactate and pyruvate from some other carbon source, you can, but not by the core recycle. Okay, now, so where do some of the new carbons come from? Well, they come from amino acids. Of all of the amino acids are potentially gluconeogenic, except the two ones circled in green here, lysine and leucine. So those are ketogenic amino acids. You can't make new glucose carbons from lysine and leucine, but in theory, you can make it from all the others. But measured repeatedly in multiple studies, some huge number of studies. Now we know the principal gluconeogenic amino acids are the ones circled in red, alanine and glutamate, that are responsible for, in the fasted state, a significant fraction of new glucose. And this is, in fact, new glucose carbon. That is, you've taken amino acid carbon and turned it into glucose carbon. So as far as the glucose carbon system is concerned, these are new glucose carbons and can be used to feed the brain, okay? But what's the problem? The problem is, in the absence of dietary carbohydrate, the brain is fed at the expense of amino acids released by transamination or simply released from muscle. So if you starve, you can use amino acids in muscle to make new glucose for your brain, but I think you can realize that eventually this runs out, right? This isn't a good circumstance. That is, you break down muscle to feed your brain. It's good for your brain, but it's not so good for other things in starvation. And in starvation, you eventually die because your diaphragm muscles don't work very well, and you get pneumonia and you die. And okay, so this is the system by which you make actual new glucose carbons. Now, I'm glad Stephanie's on the phone. So I wanted to, as a pediatrician myself, I wanted to go back to the fact that we know a lot about what happens in newborns even. So here is Benedict and Talbot, 108 years ago, who said, we find the average respiratory quotient for 74 infants. Think about that, 74 infants. You'd be lucky if anybody in a nursery today studied 5. Okay, 74 infants on the first day of life was 80, was 0.808. This value represents a fasting value not widely different from that observed during the first 24 hours of fasting man, 0.79. Now, in my life, I've studied a huge number of newborn infants, and the bottom line has always been, to my surprise, the baby comes out and everything works the way it's supposed to. Just like in adults, it just goes faster. So a short fasted newborn, okay, who has a brain, as you'll see, 1/4 the size or 1/5 the size of an adult, is using glucose and making glucose at a rate that's really substantial. And their adaptation to not getting food or not getting the glucose is just like the adult, but it happens over a matter of hours versus a day. Okay, so the newborn brain doesn't use much in the way of fatty acids and amino acids. Glucose is far and away the preferred fuel, and if you measure glucose production rates in the newborn, as I and many other people have done, the newborn glucose production rates barely meet the brain's glucose requirements. And ketones are the principal alternative fuel, and lactate there's at least one study in which lactate served as a fuel. Now, as I mentioned before, the ketone utilization is proportional to the arterial level. And here we have at the bottom 2 studies of 50 years ago, in which we know, because the experiments were done, when Peter Adam, for example, studied, aborted fetuses and perfused brain human fetuses and show they can oxidize ketones. The same was true when Krauss studied the newborn brain, with what we would now have invasive techniques. So we know, we don't have to make models, whatever. We know unequivocally the human brain can use those ketones in place of glucose if it must, okay? But the human newborn is getting a lot of carbohydrate and milk and stuff, and normally doesn't have much in the way of elevated ketone levels unless you don't give them food. And those of you remember when medicine was, enlightened, we didn't feed babies for the first 24 or 48 hours, right? Well, we stopped that after a while. Okay, so now let's look at the brain in the newborn to adult. So this is the brain weights of 700 men and 2,000 women. And if we look at the size of the brain, the newborn brain is a little less than 400 grams. By the age of 6 or 7, it's about 1,200 grams, and the adult male brain's about 1,400 grams, and the female brains is about maybe 1,250. So the point of this is to show you that if children are oxidizing glucose like adults, and there's every evidence that this is the case, okay, by the age of 6 or 7, you have to essentially supply that 100 grams of glucose or so. So if we look at brain glucose utilization in children and adults measured with PET scanning, and the data, you can imagine we have a lot of more data in adults, and we have very scattered data in children. And so the children's numbers here are all, with a big confidence interval around them. But you can see that by the time you get to be 5 or 6 or 7, you're already using glucose in your brain at the adult level. So if one is going to set recommended intakes or allowances, one needs to deal with the fact that from age 6 or so onward, you need to set the adult number or approximately. And in early infancy, you need to set numbers that are almost adults in the toddler years. Now, if you're not good at math, I've converted this to snack units so that you understand that, what this would be if you want to include it, in some other context for people who are mathematically challenged. Okay, now, does any of this matter? Okay, so back again 50 years ago, Marv Kornblath and Bob Schwartz published a book called Disorders of Carbohydrate Metabolism in Infancy. It went to 3, I think maybe 4 editions. And here's a figure from that slide. And you can first look at how, I don't know, just all the terms on this slide except the islet cell adenoma mean idiopathic. They sound like you have a diagnosis, but they all mean idiopathic. We have no idea. And if you look at children between the ages of about 1.5 years to 5 or 6 years, there was a very large fraction of hypoglycemia that was due to an entity called ketotic hypoglycemia. And this entity is due to the inability to supply gluconeogenic substrates and the inability to switch to ketone bodies. And all you have to do to prevent this disease is to feed kids late at night and don't let them go too long in the morning without having breakfast. Now, we don't see ketotic hypoglycemia anymore, at least I don't, and I don't think any people do, because we learned that you need to feed the brain. And in the very, susceptible years in toddler life, when the infant brain is consuming almost what the adult brain is, you need to be very careful in that regard. So that's all I have to say. And I would say that, the data are really very strong that the brain needs something on the order of 100 grams of glucose a day. Now you can get, as I showed you, some of this from ketones. You can get some of it from amino acids that are, that are released from muscle and stuff. So if you're setting a requirement for the population, maybe you can reduce that number because there are other sources of new carbon. However, I think you then take a risk, particularly in childhood, because children's brain is using a lot of sugar, and in addition, the stuff you don't supply is essentially permitting lipolysis to continue and proteolysis to continue to supply that carbon. So I'm not sure it's wise to set requirements of that kind. So thank you.
So thanks so much, Dr. Beer. Very interesting presentation. We can stop the slides. This is a time for questions. If you wish to ask a question, please use the chat box or raise your hand. I'll recognize you if I can see you. While you're thinking of questions, let me ask the first one to you. So, Denny, you've indicated very clearly that there are gluconeogenic amino acids, particularly alanine and glutamine or glutamate. If someone's on a low carb but ketogenic diet with a great deal of protein containing those amino acids, would those amino acids be able to provide a significant boost in new glucose?
John, I don't actually know that kind of experiment was done. I mean, I just don't know the data, but the answer is theoretically yes. So, but ketogenic diets are, at least to me, not the normal. One would argue that that's not within the normal range of diets for the general population. And in addition, as I mentioned, people on ketogenic diets, I'm sure there are those who get 3 millimolar acetoacetate and beta hydroxybutyrate, but the bulk of people don't get there. They get to 1.5 or something like this. And I would argue that that can supply, little glucose. I mean, not a huge amount of glucose. The brain does work. I mean, I think it's very clear the brain can eat ketones if you force it to. Okay, but that's not its preferred state.
Thank you. Dr. Lichtenstein has her hand up.
Yes. Well, it was really very nice to see all that stuff pulled together, basic biochemistry. But I guess one of the things that struck me was something you said at the beginning, and that was that perhaps it shouldn't be termed essential nutrient in the way we think of the micronutrients, but you refer to, I think, reference intakes. And I'm wondering if that would, for the macronutrients as a whole, not those where there are essential amino acids, essential fatty acids, that maybe we should think of it in terms of essential or reference intake as opposed to the classic essentiality.
Well, I have another slide or two in different contexts where I talk about essentiality from the human perspective, which is you need to get 2 fatty acids and 8 or 9 amino acids from the diet, or from Mother Nature's perspective, in which you get every carbohydrate, you can make every carbohydrate you need. Well, from Mother Nature's perspective, carbohydrates are more important. It didn't leave getting them to chance. So, I mean, these are, some kind of philosophical, arguments, but I think it gets down. I mean, I think what we have to remember is when nutritionists talk about requirements, they're talking about requirement from the diet. From metabolism, everything is required. I mean, you know, we can remove one amino acid or one, and things go haywire. So from the perspective of the organism, they're all required. And that's true of when you get to non-essential amino acids. You can't live without glutamine and glutamate. I mean, glutamate connects all the major fuels, you know, so it's really, in fact, Peter Reed's, rest his soul, coined the term glutamate, the essential, non-essential amino acid. That was about 25 years ago.
Thank you.
Other questions? Dr. Breer, I think you've proven that many of us have not looked back into metabolism.
I'm going to say, Pete, I would say that if you talk about this to medical students, they'll look at you very funny today because there's no genes involved. I mean, it's just, you know, you didn't mention a gene. Wait a minute. We didn't have genes when I was young. So.
Are there any other questions? Dr. Davis.
So thanks, Denny, for a very nice presentation and really emphasizing why glucose is needed for the brain. With that said, for some of us rather naive people that don't think about this and expertise is in different areas, a lot of the work that you presented was 50 years old, as you said so nicely. How much work has really been done in this area since the last DRIs?
I would, by the way, I really haven't looked at that, but essentially none, except in specific conditions. That is, you know, in certain disease states and in diabetes and things, people continue to do these kinds of studies. In injury, you know, surgeons do them, etc. But in normal volunteers, in adults, I don't really recollect hardly any. I'd have to go back and think of, you know, try to find them. And in pediatrics, almost none, because pediatric experimentation has become, you know, unpopular.
Thanks. The reason for the question is the understanding, is there likely to be a lot of new evidence or not that would change the requirement part for dietary carbohydrates? And that was really a lot of the reason why we asked to have this workshop today, is really to say, is there a lot of new evidence and other things that we should be looking at to provide to the committee and other systematic reviews that need to be done before we go to a macronutrient review?
Well, I would, by the way, I would go back, well, first to Otto Warburg's, you know, remark, which is good experiments last forever. If you get it right the first time, it's still right 50 years later. And in the case of the brain using glucose, the body of data is so huge in this, and from different, you know, different kinds of experiments. And then the PET scanning data, which all came later, right? That's all 20 plus years of age, agrees pretty much with all the balance data, but it's very hard. I mean, you know, unless people did it wrong, you know, we're talking about simple addition and subtraction. You measure what went in, you measure what came out. It's really hard to get harder data than that.
All right, I see Dr. Lichtenstein, and after that, Dr. Lynch.
Cindy brings up a very important point about, was there new data that would suggest that there might be a modification? And I'd like just to add something to that. I was on the original macronutrient panel in the late 90s. And we came up with the macronutrient distribution range sort of on the fly because we couldn't figure out how to come up with numbers within the context of the classic essential nutrients. So the essential nutrients, micronutrients. So it ended up that there was this really wide range. We didn't have systematic reviews, and somebody said, well, I know there's this paper that showed it 15% of energy people did fine, and somebody else said, well, I know, there's this one paper that at 40 or 50, whatever. And that's sort of how we came up with the numbers. So I think it would be helpful to have a better criterion for why you would establish and how you would establish the a DRI for carbohydrate that would probably be better than what we did in this sort of backfilling.
It's a complicated question. So if we look at the JCI experiment of Ollie Owen and George Cahill and Errol Marlis, and there's no question you don't have to feed people for 40 days or 60, 50 days. And the brain, these people were alert. They were walking around the clinical research center ward. They weren't, they weren't intubated and stuff. I mean, their brains were working. Okay, so the brain, no surprise, it's our highest function, has protected itself for 1 million years of mammalian evolution and, another close to 1 million, whatever it is, human evolution. The brain has used everything possible to make sure it keeps going. So you can, use alternate fuels. The question is, to me, what does the context of the normal population mean and when? Because we're used to overnight fasting. That's sort of a human habit. Okay, but is the post-absorptive state the state we should be using? We know readily, people in the hospital routinely fast for 1 or 2 days. I mean, that, is common, or have severe caloric, restriction, and they do fine, but I don't count them in the context of the everyday walking around normal population.
Dr. Lynch.
So and thanks, it was a great talk. But to reiterate what you said, the glucose is very important for our body, but dietary glucose is not required.
Well,
is that summarize?
I didn't say that dietary glucose was required. We're talking about carbohydrate.
No, I know you didn't say that, but you said that it's not required.
I don't remember saying not.
So is I think the question
all
is,
carbohydrate enters your body as mono or disaccharides. So you can eat all the carbohydrates you want, and it comes in, as a mono or a disaccharide. So we can get into a lot of.
But it's not required. It's not required for you to eat carbohydrate.
Well, that's why that's
based on your talk.
I said that's why I said we can make every carbohydrate we need, and why I prefer the terms of reference intakes or allowances. But if one decides not to take in any carbohydrate, one does that at the expense of other adaptations, which might be considered, not healthy.
Okay.
So I mean, that then you get into all these judgment requirements, and again, Alice, pointed this out. When we're talking about requirements of something you can make, you immediately go to a subjective judgment, risk versus benefit of some kind, and that's for the committee. I leave it to you. I'd rather have the carbohydrate in the diet and not worry about it, but that's me, because I'm by the way, I'm a pediatrician who started my life taking care of children with low blood sugar, as Stephanie does with some regularity, and others. So we learned there's a very easy way to prevent that.
Well, I think this discussion has really set the stage for following talks. We have a presentation that's particularly focused by Christine on infants and during lactation, and we also will have a presentation by Barbara on consequences of lower carbohydrate diets. We're a little bit ahead of schedule, so we could still take another question or comment.
Well, I just make another another comment about why I think carbohydrates, Mother Nature's most important fuel for humans. Remember, human milk contains 7% carbohydrate. You don't find that in rats, rodents, dogs, mice. Mother Nature decided it was really important to supply the carbohydrate to feed our brain.
Thank you. Again, we still have a couple of minutes if there are any other questions at this point, and we'll have a panel discussion in the end too. So why don't we move on then? I don't see any. Valerie, could you introduce our next speaker?
Sure. Our next speaker is Dr. David Klurfeld, sorry. He's an adjunct professor at Indiana University's School of Public Health and recently retired as National Program Leader for Human Nutrition in the USDA Agricultural Research Service. His research is focused on the relationship of diet and prevention of chronic diseases. And today he will be presenting on the role of carbohydrate as a delivery vehicle for nutrients. So please welcome Dr. Klurfeld.
Well, thank you very much. So Dr. Erdman gave me a very specific subject to cover, the role of carbohydrate as a delivery vehicle for other nutrients. And I know if you aren't looking at the chat box, Dr. Lichtenstein put that very comment in there that low carbohydrate diets risk being deficient in multiple nutrients. So I need to make a few disclosures. Since I retired from USDA, I'm doing some consulting, and the most relevant one is at the top here. I'm a member of the Scientific Advisory Panel for Potatoes USA. So I have a couple of slides to just frame some of the issues that I thought of as I was trying to decide what's most important for this committee to consider. And there's really no commissioner of diet labels, that there's no accepted definition of what low carbohydrate diet is. The dietary guidelines for Americans list the ANDR from the DRIs as the acceptable range of 45 to 65% of energy coming from carbohydrates. And at the lower end, if you're consuming 1,600 kilocalories a day, which is the 10th percentile in NHANES, so you're getting 180 grams of carbohydrate. And the current DRI is 130 grams a day. So the vast majority of people are not in any way getting close to what the lower limit is anticipated to be. Even with the increments for pregnancy and lactation, very few people are not getting sufficient carbohydrate by this metric. In NHANES, there are 7 or 8 nutrients of public health concern. They're all listed here. You've all seen these umpteen times in papers over the last 2 decades. Added sugars and sodium, saturated fat, dietary fiber, potassium, calcium, and vitamin D. One of the important points to consider in carbohydrate as a food source is that there are 3 grains that provide the majority of energy in the human diet, not just in the United States, but worldwide. And in fact, in Thailand, for instance, up to 74% of calories came from rice alone. And the reason for those three grains being important sources of energy is they're highly productive. They can be harvested and dried, stored for long periods. They're easily transported. They're cooked into a variety of products that appeal in different cultures, and they're very economical. So these are some of the issues that need to be taken into account when trying to decide what preferred food sources of nutrients are important in the United States. And certainly rice and maize are less important than wheat. But again, with the diverse ethnicity in our population, with Asian immigration, we have a lot more rice consumption. With Latinx immigration, we have a lot more corn meal consumption. So another aspect to consider in just thinking about carbohydrates as an important nutrient is the concept of nutrient-dense foods. Is this truly independent of carbohydrate content, or does carbohydrate simply fill in the missing calories that aren't fat or protein? The food composition database doesn't directly measure carbohydrate or sugar. It's carbohydrate by difference. It's sort of the unwanted stepchild in the nutrition family. And certainly the USDA doesn't have the budget to fill in all the blanks of doing direct analysis for sugars, for different carbohydrates, for dietary fiber resistant starch. But carbohydrate rich foods are the only source of fiber and resistant starch, and they're the principal source of carotenoids and multiple polyphenols. You're not going to find that in a primarily protein or fat providing food source. So in addition to the naturally occurring nutrients in carbohydrate-rich foods, grain flours are fortified. And the reason for that was when FDA made the decision to initiate folate fortification of wheat flour, white bread was the most commonly consumed food category in NHANES. And so 74% of people ate white bread every day back in the 1970s, before we had widespread obesity. And so there's an important question. If you're not going to recommend high carbohydrate intake, which a significant portion will remain as wheat flour products of various sorts, should not just women who are pregnant, but women who could become pregnant, should they not restrict their wheat flour intake because they'll become deficient in folate? And in rice and cornmeal or corn flour products that are distributed in federal programs to schools or nonprofits, a couple of B vitamins and iron supplementation is required. So again, and iron turns out to be a nutrient of concern, even though it isn't listed in the 7 big nutrients of concern. Iron status has actually declined in the United States over the last 10, 20 years, in parallel to reduction of beef intake with replacement with poultry intake as the primary meat source now in the American diet. So the key here is that the various nutrients that carbohydrate-rich foods provide are really poorly represented in databases. If ARS had the budget of the Pentagon, they could catch up with all of the blank spaces there, but we really don't know how much we're truly missing because of the weaknesses in the databases. So I want to take just a couple of slides to show you where we're getting carbohydrates in foods. And so the US current carbohydrate intake in the most recent NHANES is shown here. And I'm showing this in percentiles. The 50th percentile is close to the mean, but not exactly. It's really important for the committee to not view the intake as you see the sample distribution curves all the time as sort of an idealized central mean with a more or less normal distribution around them. Undoubtedly, this is a multimodal distribution, especially for sugars. In the top two lines here for adults is total carbohydrates. And remember, the RDA is 130 grams a day. So it's only women, adult women, at the 5th percentile of carbohydrate intake who aren't getting 130 grams, and they're fairly close to it. NHANES lists less than 3% of the adult population as not meeting the estimated average requirement. I've put total sugars here just to show you what a high proportion of total carbohydrate intake is provided by sugar in the American diet. And part of the reason for that is we're choosing the wrong foods. And you know that's maybe something for the dietary guidelines for Americans. But here, this is almost 20-year-old data. There's overall, in the first column, ages 2+, then children and adolescents, and the third column are adults. And what you see is grain-based desserts now provide 6.5% of our calories in the American diet. It's the #1 source of calories. And at the bottom here, the #1 source of calories in the 1980s and 90s was soft drinks, followed by grain-based desserts, which was half the intake 20 years earlier. And in the 1970s, white bread was the primary source of caloric intake in NHANES. And so white bread, which is now listed as yeast breads, is second here. The ones that are highlighted in yellow are principally carbohydrate foods. All of the other foods that are not yellow colored are mixed dishes, some of which are relatively high in carbohydrate, some of which are not. It's very difficult to assess how much carbohydrate, like tortillas, burritos, and tacos. If it's a tortilla, it's obviously mostly carbohydrate. If it's a taco or burrito, it's probably not mostly carbohydrate. So the key is here, we're choosing desserts and snacks as our principal source of carbohydrates, which is clearly not what's recommended. And so the issue is we're choosing foods that are relatively low in nutrients and high in energy, but they're not nutrient dense. And there have been a number of carbohydrate quality scores proposed over the years, and most of them have focused on energy density and fiber as a proportion to total carbohydrate. The most recent scores have been the carbohydrate food quality scores 4 and 5, developed by Adam Dranowski and some of his colleagues. And the 4 metrics in Adam's scoring system are free sugars, sodium, fiber, and potassium. And in the 5-point score, it adds whole grains. And it doesn't change the correlation very strongly. If you look at the left and right columns here, really what happens with adding whole grains is the ready-to-eat and cooked cereals look better. Almost everything else stays the same, but it shows you that vegetables here, including the starchy vegetables, score the best, and sweet bakery desserts, cakes, cookies, pies, donuts, are the worst here, and not terribly different from eating sugar candies. So there are scores that are out there that look pretty good. But I want to come back again to the concept of nutrient density. One of the shifts in the American diet is the increase in calories provided from snacks. And this is middle 2000s, but it's actually gone up a little bit. So current calorie intake from snacking is around 25% of calories. And again, in the 1970s, it was half that. And you can see low protein from snacks. Snacks here are defined in Haynes as any foods or drinks not consumed as part of a meal. So what you'll see is there's a lot of sugars which includes soft drinks, but sweet snacks as well. And one thing that surprised me here is that this long bar at the bottom of alcohol, most alcohol in the United States is not consumed as a glass of wine with dinner. You know, it's people going to a bar or having 2 drinks before dinner. And so surprisingly low in fat, and certainly not surprising that it's low in fiber. But if you look at micronutrients, it's adequate in a couple of micronutrients, but low in the majority of the standard micronutrients, and fairly low in some. You know, if the energy here in the red line is at 24, 25%, several minerals and vitamins are well below that. So the proportional contribution of snacks to micronutrient literature leaves a lot to be desired. So, of course, you all haven't been living under rocks for the last 2 decades, and you know that low carbohydrate diets have gotten a lot of publicity, and sugar has replaced fat as the new dietary devil. And so you can see in the last dozen years or so, carbohydrates have dropped by a couple of percent. This represents a decline of 21 grams per day, and it's a statistically significant decrease in carbohydrate intake. And it's been replaced primarily by fat intake, which is the blue line here. And so it represents not just a trade-off, but an increase in calories and by fattier foods. So again, the wrong choice of foods that are mixtures of fats and carbohydrates. Interestingly, if you look at this green line here, that's added sugars. There's been a real decline in added sugars. Again, it's a 2 percentile decline, and it's primarily a reduction in sugar-sweetened soft drinks. That's a real decline that has been consistent over time. So there have been a few analyses of what carbohydrate restricted diets do to micronutrient intake and status. It was actually a systematic review published a few years ago. The problem is that the people who did the original studies never intended to be subjected to a meta-analysis. And so there were 10 studies, 7 RCTs, 5 of which were Atkins-style diets, 2 were paleo diets, 2 were in uncontrolled Atkins-type diets, and 1 was a cross-sectional study. And the carbohydrate intake in these 10 studies ranged from 4 to 34% of calories over 2 weeks to 2 years. And in one of the paleo studies, there were iodine deficiency symptoms reported. And there was also the risk of multiple vitamin and mineral deficiencies in the dietary reports from these studies. And if you look just at the RCTs, they're shown here. The 7 RCTs are not all represented on this slide. Some reported, nobody actually measured nutrient status. This was really dietary histories from the 7 RCTs, and not all of them measured all of the nutrients. And so in most of the studies, nutrient in the diet, not necessarily intake, but nutrients reported in the diet went down, and only in a couple of studies did nutrients go up. And it was the exception where nutrient availability in the diet was increased. So basically, magnesium and iron went down. Most of the other nutrients, they went down as well. Vitamin E sort of half went up, half went down. Nothing consistent there. But there've been a number of studies developing menus for carbohydrate restricted studies. And these next 2 papers that I'll show you were developed. The first author is a clinical dietitian whose practice specialty is using restricted carbohydrate diets. And she developed low carbohydrate diets here. And these are diets that provide less than the RDA of 130 grams per day. This is done in New Zealand. The diets are not hypocaloric, so they're not weight loss diets, which a lot of people following low carbohydrate diets are doing it for weight loss or diabetes control, but not these particular diets. All the meal plans exceed the Australian, New Zealand nutrient reference values, except for iron. And some of the meals exceeded saturated fat limits. She was able to actually get enough fiber from 10 servings of vegetables a day, limiting fruit, and adding a lot of seeds and nuts to the diets with 0 whole grains. She points out she could only develop 2 diets, 2 days worth of diets. And it was extremely difficult to do that. And she did the same thing in another publication here last year with an even lower carbohydrate diet for adolescents, less than or equal to 80 grams per day. And I have a quote here. This was selected as the midpoint between 130 grams and a ketogenic diet limit of 50 grams. And so I wasn't the best student in arithmetic, but I don't see 80 grams as the midpoint between 50 and 130. It's interesting that the carbohydrate in this diet was mostly sugar and not starch. But in this diet actually included some whole grains. And in this instance, met the Australian, New Zealand nutrient reference values. So you can do it, but it's really difficult. And finally, there was an Australian study with even lower carbohydrate intake and in weight loss diets for adolescents. And here, the carbohydrate limits were 30, 50, and 120 grams. That corresponds to 7, 13, and 26% of energy. The fiber is 18, 21, and 29. That's below the adequate intake that's set in the United States, but it's at or above the NHANES average intake. Saturated fat does exceed the limit in all diets. A lot of servings of low starch vegetables, a lot of nuts, and low sugar berries like strawberries in particular were used for this. Again, the first author pointed out there are just limited options, and it was very difficult. None of these three diets that I showed you in these last three slides were actually fed, so they weren't able to comment on acceptability, and they pointed out there's a lack of variety in their menus. So even though the dietitians writing these papers were proponents of these diets, they basically spent a good part of the discussion saying how they weren't sure anybody could follow these diets. Well, there actually were some athletes who followed these diets, and this is a 12-week study for male endurance athletes, excuse me, who were either assigned to a high carbohydrate diet, 65% of calories, or a low carb ketogenic diet, no more than 50 grams per day. And about half the nutrients were higher in the high carb diet, half the nutrients were lower in the low carb diet. And I've listed them all here on the slide. As you would expect, carbs and fiber and sugar go up, but sodium, magnesium, iron, copper, manganese, thiamine go up on a high carb diet. On a low carb diet, saturated fat, protein go up. You have a higher omega-3 to 6 ratio, more selenium because they're eating more meat, and more vitamins A, D, E, K, B12, pantothenic acid, biotin. They actually measured and saw decreased mean corpuscular hemoglobin, mean corpuscular hemoglobin concentration in the low carbohydrate participants after 12 weeks, which didn't change in the high carbohydrate participants. And that's an observation reported with no explanation there. And these people were eating 2,800 calories a day because they're endurance athletes. So it's not clear if you could extrapolate to an 1,800 calorie a day diet, which is what most of us ought to be eating. Coming back to the United States in Haynes here, this chart shows you from Haynes what the healthy eating index is with the current red circles. And you can see here that we don't do too well as a general population. Even vegetarians don't do a lot better. But look at the two lines with the blue arrows on the left here. We have low grain consumers, almost as good as vegetarians, but not that good here on the red dot. And low grain is defined as less than 10 percentile of total grain intake. And then if you look at the next line with the blue arrow here, restricted carbohydrates is actually better than average, than the average American. And restricted carbohydrate here is less than 45% of calories. And the modeling here is replacing one serving of foods higher in some of the nutrients of concern, like added sugars or sodium or saturated fat or refined grains, just replacing a single serving. And you can get 2 or 3 points on the healthy eating index. And I want to point out that for a low carbohydrate diet, which was defined here as less than 25% of calories, there were only 16 people who reported consuming that out of more than 32,000 consumers in Haynes. So, we just don't have enough data to really say anything worthwhile about low-calorie diets under 25% of calories. And I'm going to finish up with one slide that's actually fairly old. It's almost 25 years old. This came from the Tufts Human Nutrition Research Center on Aging, looking at the variety of vegetable consumption, except potatoes, in panel A on the left. And the more variety of vegetables consumed, the lower body fat. And on the right side, the greater variety of an odd combination of foods. This is snacks, sweets, condiments, entrees, and carbohydrates. So this includes a real gamut of foods like ice cream, cookies, candy, all white and sweet potato products. So roast potatoes, potato chips, rice, biscuits, white bread, dark bread, which in the 90s, we didn't have a lot of information on whole grains. So it includes whole grain products and crackers, but statistically significant increase in body fat. They didn't report body weight in a graph that was easily shown, but it suggests here that higher vegetable consumption seems beneficial, while higher simple carbohydrate seems detrimental for body fatness, at least. And I'll stop there. Thank you.
Thank you very much for this presentation. Are there questions for Dr. Clearfield? Dr. Lynch.
David, when you've mentioned carbohydrates throughout this talk, how is dietary fiber excluded, which is often a carbohydrate, and just like in milk, a third most abundant thing in the milk is the milk oligosaccharides, which aren't digestible by the host.
Yeah, that's a really important point, Chris. Carbohydrates on the FDA label are under, dietary fiber is under carbohydrates. But when you look at NHANES data, carbohydrate intake excludes dietary fiber. And, if you're looking at 180 grams of carbohydrate, 150 grams of carbohydrate a day, and you're talking about 15 to 18 grams of fiber, it's less than 10% of total carbohydrates. It's almost irrelevant. And, essentially, nobody in the United States consumes the adequate intake of dietary fiber, which is 25 to 38 grams a day. We have maybe a couple of percent of the population is consuming adequate fiber. It's really problematic, and because you need to get fiber from either whole grains or fruits or vegetables, and Americans just aren't eating enough of those categories of foods, which provide lots of other nutrients.
Well, that's what I was wondering when you showed that figure about the the vegetables sources of carbohydrate, and because they're carrying along the fiber too.
Yes, you're absolutely right.
That weight loss.
That analysis is confounded, but we don't have any data to say how much it's confounded.
Okay. You have another question from Dr. Erdman?
Yes. So David, is there a universal agreement on how many grams a day is a low carb diet? You mentioned 50 in one study. Do we have a definition?
No, there is no generally accepted limit for that. I think almost everybody accepts 50 grams per day as a limit for being able to induce ketogenesis. A lot depends on the individual's weight and body fat percentage on what it's going to take to flip metabolism to ketogenesis. But I think 50 grams is a reasonable estimate.
Thank you.
Dr. Lichtenstein.
I think Dr. Brought up an important point. Where would the recommendation come from, or if it wasn't from the DRIs? And there is no mechanism within the system to come up with something like that. But there's one thing, listening to Dr. Klurfeld's presentation, that occurred to me is when I think about protein and fat, I think about essential amino acids and fatty acids, which are sort of separate. In terms of carbohydrate, you don't think in those terms of an essential monosaccharide, but perhaps we could think of it in terms of fiber, because it's those foods, the carbohydrate-rich foods into the fruits, vegetables, and whole grains. I would also add nuts and seeds and legumes. They do contribute a fair amount of carbohydrates, so just something to think about.
Yeah, I unfortunately didn't show you any of the slides of these carbohydrate quality indices, most of which, other than Adam Jernowski's, which I think is actually an improvement over the previous ones. And Adam does include fiber, but the earlier ones were basically looking at the ratio of fiber to total carbohydrates. And certainly now with the inclusion of chronic disease health endpoints since 2017 as a basis for setting DRI values, nothing I talked about really is going to be as important as what Denny Beard told you all on setting a requirement. But what I talked about is certainly going to have to be considered for relationship of carbohydrate-rich foods to chronic disease endpoints.
I can't resist making a comment. I mean, the topic that you were very kind to try to address in this presentation was the idea of carbohydrates as a delivery vehicle for nutrients. And one of the things that comes through loud and clear in your presentation, and also is, I think, implicit in the questions that you've gotten, is this idea that the answer to, the value of carbohydrate as a metric for nutrient delivery depends so much on what we're talking about in terms of carbohydrate. I'm starting to wonder if we're asking the wrong question here. That people, depending on the perspective, can talk about fiber. You in some of your slides talked about naturally occurring nutrients in some things, but then we evaporate into a conversation about added sugars or total sugar as a part of carbohydrate. What do you think? Should we continue this kind of pursuit of an appraisal of carbohydrate through the lens of nutrient density?
Nutrient density is an important concept that really has never gained traction in the dietary guidelines for Americans. It would take a lot of education. I certainly think our colleagues can handle it. I think dietitians can embrace it. I'm not sure the general public can really benefit from it without an education campaign. But I think it's essential. I'm certainly going to have carbohydrates for lunch today, and there's going to be sugar from the fruits that I'm going to have after my whole grain bread. But white bread is still one of the more popular foods, and they've been displaced by grain-based desserts, and that's really problematic for the health of North Americans, because I'm guessing Canadians aren't that different in their intake from people in the US. So I really do think that getting people to embrace the concept of nutrient density is something that can benefit public health.
Are there any other questions before we head to a break now? I know it's been a long morning to be on Zoom already. Okay. Seeing none, then shall I give it one more minute? Just if you haven't been following the dialogue that's been going on in the chat, I would really encourage you to do it. It feels like we have a very interesting kind of line of thinking going on in the chat. But seeing no more questions, I think we should perhaps start on our break. So what we're doing now is having a 20-minute break. So by my calculation, that means we're coming back at around 10:56, 11 o'clock. Shall we say 11 o'clock, round it up? Yeah, okay.
Yeah.
Okay, so let's take a break now and head back at 11 o'clock for the next presentation. Thank you.
Great.
webinar attendees, speakers, and standing committee members. Our next speaker in this webinar series is Dr. Barbara Gower. Dr. Gower is a professor at the Department of Nutrition Sciences and serves as director of the Metabolism Core Lab at the University of Alabama at Birmingham. Her research focuses on the interplay between diet, endocrinology, and metabolism, and their relation to chronic metabolic disease, with expertise in evaluation of body composition, body fat distribution, insulin sensitivity, and beta cell function. Today, Dr. Gower will be speaking about the consequences of carbohydrate restricted diets on metabolic function. Welcome, Dr. Gower. Thank you.
Thank you, Sai. Thank you, everybody, for being here. I've been enjoying this conference. Okay, I'm going to talk about restriction of dietary carbohydrates and the impact on metabolism. And I'm having the same trouble. Whoop, there we go. Okay, here we go. So let's put this into a little bit of context. What did humans evolve to eat? Well, we were hunter-gatherers. We ate meat, nuts, etc., up until about 10,000 years ago when we developed agriculture. But that, in evolutionary terms, that's the blink of an eye. So I would argue that humans are not adapted yet to an agriculture-based diet. Carbohydrate-restricted diets are not dangerous. There's a lot of misconceptions about them. Protein consumption is not excessive. It's usually at the same normal level, 15 to 20%. Ketones are a physiologically relevant fuel source that can be used by the brain very efficiently. They require a lower oxygen requirement for use as a fuel, and so they're actually a very efficient fuel. The use of ketones as a fuel, or the term ketogenesis or in ketosis, none of this implies ketoacidosis. Ketoacidosis is a very pathological condition that occurs under very specific physiologic circumstances. The use of ketones as a fuel is physiologically relevant. It only implies a very mild increase in circulating ketones. All of us listening to this presentation are producing some ketones right now. And all that happens when you go into ketosis is the level of ketone production increases slightly, but it's still in the physiologic range. And finally, the liver makes lots of glucose. As Denny Buer told us earlier today, we make several hundred grams of glucose a day. So the brain will never be without glucose. According to the literature, the Paleolithic diet was about 30% carbohydrate, and most of this came from fermentable fiber. And I think it's important to point out that humans evolved to store fat. We don't have a mechanism for storing carbohydrate. We can store limited amounts of glycogen in the liver and skeletal muscle, around 400, 500 grams, which might be enough to get you through one day. But this is literally the icing on the cake. Carbohydrates were available historically, probably on a seasonal basis. We had access to a little bit of fruit and honey. And we might have eaten this in the summer, much like a grizzly bear would to fatten up for the winter. But most of the year, we were relying upon other sources of fuel. So we aren't really evolved to consume large amounts of carbohydrate. So what happens if you take carbohydrates out of the diet? This study here was a crossover study conducted at the weight-maintaining level with a high-carb diet on one hand at 75% energy from carbs and a high-fat diet at 75% energy from carbs. And this is if you look in the upper left here where my cursor is, this is the time of a postprandial period, and this is insulin. One of the most phenomenal differences between a high carb and a low carb diet is circulating insulin. You can see in the high carb diet in the blue, you get a tremendous spike of insulin following a meal, whereas it's quite a bit more modest on the red line, which is a low carb diet. And this tracks glucose, which is also strikingly divergent across the course of a meal. And then over here in the last panel, you have capillary beta hydroxybutyrate, which is a ketone, and this is days on the diet. This was a 14-day intervention. And you can see in the high carb diet, the green line, ketones stay very low, whereas they increase modestly. They get up to 2 millimolar, which is really quite low. And this is on a 75% fat diet, which is probably under 10% energy from carbohydrates. But again, I think what I want to emphasize here is the biggest metabolic change that's occurring with a carbohydrate restricted diet is this decrease in circulating insulin. When you eat a carbohydrate restricted diet, almost by definition, you're eating more dietary fat and you're oxidizing those fat as a fuel, and some of them are being converted to ketones. All of this is regulated by insulin. So let's take a quick look at what's going on. This is an overview of beta oxidation of fatty acids. What beta oxidation is sequential lysis of 2 carbon units as acetyl-CoA. These acetyl-CoA molecules then have any number of fates. Over here on the right-hand side, you can see that one possibility is they can be re-esterified. They can form fatty acids again. They can enter the TCA cycle and produce ATP and CO2, or they can be converted to ketone bodies. Which of these pathways the acetyl-CoAs take is dependent in a large part on circulating insulin, which is dependent in a large part on carbohydrate intake. The production of ketones is essentially titrated to regulate the production of ATP from fatty acids. As fatty acids go up in the circulation, either from mobilization from adipose stores or from dietary intake, more ketones are produced. There's a limit to how much carbon you can run through the TCA cycle. And so the production of ketone is, in a sense, a safety valve. It's a way to get rid of excess acetyl-CoAs. And its production is actually very important. And this is why. Fatty liver occurs when you have the simultaneous occurrence of elevated insulin and elevated free fatty acids. Ordinarily, you don't have this. So if you're in a fasted period, your insulin will be low, your free fatty acids will be high because you're mobilizing stored fat. And then the reverse occurs when you eat. So it's very pathological that you would have an elevation in circulating free fatty acids at the same time that you would have an elevation in circulating insulin. But we do see this today, and it's because of human lifestyle and diet. People are not calorie restricted. They're eating large amounts of calories and large amounts of carbohydrates. Obesity is rampant, insulin resistance is rampant. And so we do in fact see elevations in circulating free fatty acids and insulin at the same time. And that's why fatty liver is becoming a large problem in human health today. So how you can get rid of fatty liver is to engage on a carbohydrate restricted diet. And this heading here says ketogenic diet, but you can do the same thing with ketogenic would be considered an extreme version of a carbohydrate restricted diet. But regardless of how much you restrict carbs, you will at some level decrease serum insulin. And when you decrease serum insulin, you regulate the fate of those acetyl-CoAs. So if you look here in the red circle, when insulin is low, the acetyl-CoAs will go towards beta-hydroxybutyrate. Where they won't go is over here to this side, which is the TCA cycle, where they can also get diverted to de novo lipogenesis. So these are your two choices. You can either make more fat out of the acetyl-CoAs, or you can get rid of them as ketones. And this switch is thrown by insulin, which in turn is regulated in large part by carbohydrate consumption. Now, I want to say a word about the production of beta-hydroxybutyrate. There's a lot of interest in ketones right now. You can even buy them. They're sold as a nutritional supplement or as a food. But to be honest, we don't really know that much about the benefits of ketones per se in human health. What we do know is the process of producing them is beneficial. There is a strong association between ketone production and a healthy liver. When the liver stops producing ketones and starts oxidizing acetyl-CoA, that's when fatty liver occurs. So I think what we're looking at is that dietary carbohydrates regulate hepatic metabolism, which in turn regulate chronic disease through influencing insulin. Individuals with type 2 diabetes almost invariably have fatty liver. So I'm going to show you some data from the literature on a variety of low carbohydrate diet interventions. And what I want to emphasize before I do this is that these are always going to be more than just carbohydrate restriction. If you take carbohydrates out of the diet and you don't replace them with anything, what you have is a hypocaloric diet. So you have participants that are in negative energy balance, which means they're losing weight. And they'll also be producing ketones, but this will be primarily from stored fat. The other way you can do this is take the carbs out and replace them with fat. This would be a eucaloric diet, and it would also be ketogenic because you'd be producing ketones from exogenous fat. And also, I want to emphasize that the literature there's a quite amount of variability in terms of what the carbohydrate restriction is. In some cases, a carbohydrate restricted diet is 10% energy from fat, up to almost 50% energy from fat. But these are all being presented relative to a control diet that is higher in carbohydrate. So this study here actually used 47% energy from carb as their low carb diet and compared it to a high carb diet. And what they were looking at is de novo lipogenesis, which is what you're seeing on the y-axis here. And the reason I'm showing you this slide is I want to illustrate the role of insulin in de novo lipogenesis. If you look at the white histograms, this one and this one, these are lean, healthy, normal insulin individuals on a low-carb diet versus a high-carb diet. And you can see even in lean, healthy people, just switching diet composition switches de novo lipogenesis. The same is true in obese individuals with normal insulin levels. But when you get up into obese individuals who are hyperinsulinemic and probably insulin resistant, you don't see a big effect of diet. So what's happening here is that the high insulin is trumping even the diet. The short-term exposure to low carbohydrate is not enough to lower insulin significantly, and you see that de novo lipogenesis continues. One of the most profound beneficial effects of carbohydrate restriction is the circulating lipid profile. The lipid profile is actually used in some studies as a marker of compliance with a carbohydrate restricted diet because it's so well established that the lipid profile improves when you carbohydrate restrict participants. So this particular study was done looking at, I think it was, let's see, 8 weeks maybe. Yeah, 12 weeks here. 12 weeks of either a very low carb ketogenic diet or a low fat diet. And the peach colored bars are the low carb diet. So if we just take a look at the lipids, here's triglycerides, you see that the peach colored bar shows a dramatic decrease in triglyceride, much greater than the low fat diet, which is the lime green bar. HDL, on the other hand, goes up. This is your good cholesterol. ApoB, which is your LDL apolipoprotein, goes down with the carbohydrate restricted diet. Small dense LDL, which is the atherogenic particle, goes down with the carbohydrate restricted diet, up with the high carb diet. And total circulating saturated fatty acids go down dramatically with a carbohydrate restricted diet, much more so than with a low fat diet. So despite the fact that these participants are eating actually quite a bit of saturated fat, their circulating levels of saturated fatty acids actually go down much more than with the low-fat diet. This is these data here are showing postprandial triglyceride in patients on a carbohydrate restricted diet versus a low-fat diet. And what you can see is this is baseline with the filled circles on the left here down to 12 weeks with the open circles. This is the change in postprandial triglycerides with a carb-restricted diet. And on the right-hand side here, we're looking at a fat-restricted diet, and you can see there's absolutely no change. Another interesting outcome with carbohydrate restriction is its effect on both resting and total energy expenditure. So this study was done in a weight maintenance period. After weight loss, it was a 4-week weight stabilization period with a low-fat diet, a low glycemic index diet, and a very low carbohydrate diet. And what you're looking at is the change in energy expenditure in kcal per day. This is resting on the left and total on the right. And if you just look at the light blue boxes, these are the means for the groups. And as you can see, there's a stepwise increase in resting energy expenditure with carbohydrate restriction. The lower it gets, the higher is the energy expenditure. And this is more dramatic even with total energy expenditure than it is with resting energy expenditure. And these are data from the same study. This is looking at RQ, or respiratory quotient, which is the inverse of fat oxidation. So what you're seeing is the lower bar would indicate more fat or greater fat oxidation, lower RQ. So you see the RQ decrease in a stepwise manner as dietary carbohydrate restriction increases. So it makes sense. They're eating less carb and more fat, so they're burning more fat as fuel. Another interesting effect of carbohydrate restriction is selective depletion of ectopic fat. Ectopic fat, by definition, is fat that's deposited somewhere where it doesn't belong. So a few examples of that are visceral fat, liver fat, heart fat, pancreas fat, and intermuscular fat. This is fat that's actually inside the body, the muscle. None of those are good, and they all have adverse effects on health. So this study we're looking at here was a study conducted under a weight-maintaining condition, looking at a 55% versus a 43% energy from fat diet. And this is the decrease in visceral fat over the 8-week controlled diet intervention period. And there's a highly significant decrease in visceral fat. This is a CT scan. If you look at where my cursor is, the visceral fat's the fat inside the body wall here. So this is fat that you don't want. It's highly correlated with metabolic disease. And we get a highly significant decrease in visceral fat with the carbohydrate restricted diet, and no change or a slight increase in visceral fat with a low fat diet. These participants were then put on 8 weeks of the same diet at a weight loss level, about 1,000 kcal per day deficit. And what happened was the participants on the low glycemic load diet lost significantly more total body fat than did the participants on the low fat diet. And what's interesting about this is they did not lose more lean mass. Lean mass was the same. So it seemed as though there was a protection of lean mass and a selective depletion of body fat on a low glycemic load diet. This was controlled feeding. All the patients received diets at a individually calculated energy deficit. So what we're seeing here is, despite being fed at the same calorie level, essentially, we see more fat decrease with a low glycemic load diet. This was a similar study done except as a crossover design. So 40% versus 55% energy from carbohydrates as a crossover in women with polycystic ovary syndrome. But the results were similar in that we saw a selective depletion of ectopic fat. So down on the bottom row here, we see greater loss of visceral fat on this panel in the reduced carbohydrate diet. No change when the women were switched over to the low fat diet. Selective depletion of intermuscular adipose tissue. That, if you look at the MRI scan in the upper right here, you can see this marbling of fat inside the muscle. This is a bad fat. It's associated poorly with insulin resistance and physical function. And the women lost that fat, even though this is a weight-maintaining diet and they didn't lose weight, they lost that fat, the thigh intermuscular adipose tissue, on the reduced carbohydrate diet, no change on the standard diet. When we looked at lean mass, which would be muscle and organs, we saw a significant decrease on the standard or the low fat diet, but no change on the reduced carbohydrate diet. And these are the results, the metabolic results from the same women. Again, these are women with polycystic ovary syndrome, so they tend to have elevated testosterone and insulin resistance. And what we found is when they were on the lower carbohydrate arm of the study, they showed significant decrease in fasting glucose, fasting insulin. Also, they saw an increase in fasting glucagon. They saw a decrease in fasting testosterone. They saw an improvement in beta cell function, improvement in insulin sensitivity, and lower insulin resistance. So a lot of metabolic benefits with 8 weeks of a 40% carb diet in a weight maintaining situation. These were data done with children or adolescents with fatty liver disease. And they were put on an ad libitum diet that was either fat restricted or carb restricted, but they could eat as much as they wanted. And what you see is when the children randomized to the carb restricted diet showed a significant decrease in liver fat, nothing happened to the group on the fat restricted diet. And the HOMA-IR index of insulin resistance improved dramatically on the carb restricted diet, or well, it was significantly lower on the carb restricted diet at the end of the study than on the fat restricted diet. And these are data from older adults. These are men and women with obesity over the age of 65. 8 weeks of a non-restricted or ad libitum weight maintaining level prescription of a carbohydrate restricted or a fat restricted diet. And what we saw was selective depletion of visceral adipose tissue. It dropped significantly in the very low carb diet, no change in the low fat diet. Selective depletion of thigh intermuscular adipose tissue, significant decrease on the low carb diet, no change on the low fat diet. But when we looked at the subcutaneous adipose stores, there was no difference between groups. So what we're seeing is that the carbohydrate restriction selectively depletes the undesirable adipose tissue depots. So how does this happen? You know, we're seeing effects on ectopic fat, on energy expenditure, and so forth. How does this happen? We don't know for sure, but my suspicion is that the endocrine system is involved, and primarily the shift in insulin glucagon. We see a big drop in insulin and we see an increase in glucagon. So the ratio of those two hormones changes. Insulin is a storage hormone. When insulin's high, you're going to store fuel. Glucagon is a fuel mobilizing hormone. So if you shift the ratio of these two, I think it facilitates mobilization of fuel. In terms of the selective deposition of the ectopic adipose, again, we don't know. But what I suspect is going on is de novo lipogenesis. You saw those data that I showed earlier, that with a high carb diet, even in healthy individuals, you're always making some fat. You're making palmitate in particular, and that's easy fat to store. And I think it just ends up getting stored in the organs. We don't know this, but that's our working hypothesis. Other hormonal changes have been reported in the literature in response to carbohydrate restriction. A decrease in ghrelin and a decrease in leptin, increase in 24-hour cortisol excretion, and changes in the thyroid axis. In some cases, a decrease in free T3, but in some cases, increases have also been reported. So there seems to be a lot of variability. One place where carbohydrate restricted diets are profoundly beneficial is in patients with type 2 diabetes. And I'm going to show you some data on the next slide from 46 patients with diabetes that were randomized to a low carb or low fat diet for 8 weeks. They lost weight, but the weight was identical between the two groups. So this is a low carb group on the left, week 0, week 8, and this is a low fat group. They both lost about 8 kilograms of body weight. So that there's no difference in body weight loss between the two groups. But if we look at metabolic outcomes, systolic blood pressure, diastolic blood pressure, and hemoglobin A1C all declined significantly with the low carb diet and did not change or went up slightly with the low fat diet. The percent of patients with at least a 50% reduction in medication use was significantly greater at 70% in participants on the low carb diet versus the low fat diet. There are numerous studies in the literature with showing the results from the use of a low carb diet in individuals with type 2 diabetes. This is the results from another one. What we're looking here is 24-hour glucose levels over the course of the day, 24-hour insulin levels. You can see that they're much lower, glucose and insulin both, when the patients are placed on a low carb diet. These data are from a euglycemic clamp looking at whole body and hepatic insulin sensitivity, dramatic improvement in whole body insulin sensitivity, a trend for a decrease in hepatic glucose production. This hepatic glucose production is interesting because this would be your fasting glucose. And what we see with carbohydrate restriction in patients with type 2 diabetes is they show a decrease in fasting glucose, not just postprandial glucose. So it's not just that they're not eating the carbs, their fasting glucose goes down too. So somehow the liver is getting reprogrammed. This study here was also looking at hepatic glucose production. This was a crossover design and it was a weight loss design. So it's messy and tricky to interpret, but they got a highly significant main effect of the low carb diet on hepatic glucose production, which is what you're looking at in the histograms here. The patients who went on the low carb diet first, the green bars showed a decrease in hepatic glucose production that went up a little bit when they got switched to low fat. And the other group saw a decrease in hepatic glucose production due to weight loss, but they saw a further decrease when they got switched over to the carbohydrate restricted diet. So I think this is important because this shows, again, this sort of rewiring of hepatic metabolism when you take the carbohydrates out of the diet. The final chunk of information I'm going to share with you today has to do with the race specificity of the response to carbohydrate restriction. We noticed years ago when we did a weight loss study with healthy premenopausal women and we followed them, this was the weight loss maintenance phase, we looked at the free living change in percent body fat based on free living diet and on baseline insulin sensitivity. And we found that within African-American women or Black women, the women who were really insulin sensitive and ate a high glycemic load diet gained more weight. There was a significant interactive effect to those two. So if you're sensitive to insulin and you eat an insulin stimulating diet, you gain weight. But the same was not true in white women or European American women. So why is this? Well, we were able to sort this out. It turns out the why is because African Americans secrete a lot more insulin. So this is an intravenous glucose tolerance test here. And you can see in the upper panel, glucose is identical in both Blacks and whites. But if we go down to the lower panel, this is insulin. You see that insulin, this is the first phase, this first big peak is the first phase insulin secretory response, is fourfold higher in the African Americans than in the European Americans. If we look at C-peptide, which is actual secretion, it's twofold higher. The reason insulin is fourfold higher is there's also an ethnic difference in hepatic insulin extraction. So African Americans secrete more insulin, they clear less insulin, and their postprandial insulin is higher. We looked at a number of SNPs or genetic variants in genes that are related to beta cell response to glucose. And we found that African Americans had significantly more of the SNPs that confer heightened beta cell response to glucose than did non-Hispanic whites or Hispanic Americans. So African Americans have higher postprandial insulin for a multitude of reasons, which could be why they respond, I would say, disproportionately to a high carbohydrate diet. So we reanalyzed the data I just showed you, except we substituted the high acute insulin response or low acute insulin response. We dichotomized the data both based on those two variables rather than race. And there was no significant race effect when we analyzed the data this way. What it is individuals who have a high insulin response and are highly sensitive to insulin gain more weight in the free living situation over a 1-year period. So it's all endocrine. There's no unique effect of race that can be teased apart from insulin. I think that the sensitivity of African Americans to diet has to do with their elevated postprandial insulin response. So we looked to see if this would work on the weight loss end of it. We did a weight loss study in Black and white Americans, and they were very well matched for age, sex, weight, fat. The only difference was the acute insulin response, which was higher in the African Americans, almost twofold higher. And what we found was that Blacks, but not whites, showed a diet specificity in response in the weight loss response to the two diets. So what we're looking at here is the loss of fat mass in kilograms over a 16-week intervention period. And if you look at the white bars, which is the white individuals, this is the low-fat diet and the low-carb diet, there's no difference. They both lost about the same, almost around 5 or 6 kilograms. But if you look at the African-American individuals, they lost 3 kilograms of body fat on the low-fat diet, and they lost 6 kilograms of body fat on the low-carb diet. So it does seem as though, with regarding weight loss, African-Americans would benefit disproportionately from a carb-reduced diet. Hispanics are also sensitive to dietary carbohydrates, but for a different reason. Hispanics are highly prone to liver fat. This is showing the race difference in liver fat based on total body fat, and it's higher in Hispanic, which is the red line, in both men and women. And the reason for this is Hispanics they have a high prevalence of a polymorphism in the PNPLA3 gene, which is a gene that is involved in the mobilization of fat droplets from the liver. If this gene has a carbohydrate response element, this study looked at the effect of free-living carbohydrate intake on hepatic fat fraction in individuals with the 3 different genotypes. This is the wild type genotype, the heterozygote, and this is the polymorphism that confers liver fat here on the bottom. And you can see that in this GG genotype, the greater carbohydrate intake, the greater liver fat. And the same was true if the data were plotted with total sugar intake. So Hispanic individuals and African-American individuals both seem to be sensitive to dietary carbohydrate intake. And of course, these are 2 groups that are disproportionately burdened with obesity and diabetes. So I just want to say a few words to kind of pull it all together. I know that carbohydrate restriction is a highly controversial field, and I've been working in this area and thinking about it for a long time. So I can give you my synthesis, I feel, of what the literature say at this point. Ketogenic diets are incredibly useful for weight loss. They're generally consumed at the hypocaloric level. And in this case, fatty acids are mobilized. They're converted to ketones, and this provides fuel for the brain. So if you ever talk to someone who's lost a lot of weight on a ketogenic diet, they'll tell you that they weren't hungry and they felt great. And that's because their brain, their perception of fuel availability actually was fine as long as they were mobilizing fat and producing ketones. Ketogenic diets are incredibly therapeutic for individuals with type 2 diabetes. There's no question about it. These are individuals who have what you might consider defective glucose metabolism. They have some inability to metabolize glucose. And any condition such as metabolic syndrome or insulin resistance that shares this defect in glucose metabolism, or anyone who has hyperinsulinemia, can stand to benefit from carbohydrate restriction in the diet. However, carbohydrate restricted diets are also beneficial for lean, healthy individuals. What we saw today was that you get a more favorable lipid profile and a more favorable body composition, by which I mean selective depletion of ectopic adipose tissue. Carbohydrate restriction may be particularly beneficial for groups at elevated risk for metabolic disease due to factors conferring sensitivity to carbohydrates. In the case of African Americans, high level of postprandial insulin. In the case of Hispanic Americans, polymorphism in the PNPLA3 gene and a propensity to deposit liver fat. Glucose metabolism is going to vary widely with activity level, physiological condition, genetic factors, and metabolic health. So if you're going to ask the question about a requirement for carbohydrate, I tend to think of it more as a tolerance for carbohydrate. Individuals who are lean and healthy and active can tolerate a much higher carbohydrate diet than individuals who have some degree of defective glucose metabolism or some type of metabolic disease. And I think the key points for discussion are some that we've already touched on today, the main one being carbohydrate quality. You can't really put a grain-based snack food in the same category as a starchy vegetable. I think when we talk about carbs and their place in the diet, we really need to distinguish between those two. I also think that the ability of carbohydrates to impact metabolism depends a lot on energy balance. If you're overeating and gaining weight, I think excess carbs are a lot more damaging than if you're losing weight or you're in energy balance. There's no question that there's interactive effects of dietary carbohydrates, dietary fat, and energy balance. Dietary fat has a bad name because of its perceived role in metabolic disease, but in fact, it's a really benign fuel. The only way dietary fat can be bad is if it's consumed in excess with excess carbohydrates in a positive energy balance situation. If you put someone on a 100, well, it's not feasible, but let's just say a very high fat, low carb diet, it's incredibly therapeutic. There's not going to be a negative effect of eating a high fat diet as long as carbohydrates are low. And finally, the benefits of carbohydrate restriction in the context of metabolic health. It's going to differ wildly depending on whether you're talking about individuals with type 2 diabetes and obesity versus healthy, lean individuals. So I think that's all I have. Thank you.
Thank you, Dr. Gower, for that fascinating talk and some compelling evidence on carbohydrate restriction as well as low carbohydrate diets and the metabolic and endocrine benefits. I think in the interest of keeping us on time, I'm sure this topic is going to have a lot of questions, and we can address them with the panel and move on to the next topic. But I'm sure there's going to be a ton of questions for you, Dr. Gower, so we'll be sure to address them as part of the panel. So again, thank you. We did give you a very extensive chart, so we appreciate that you covered them, and we will go to questions in the panel. Thank you.
Yes, thank you. It's a pleasure to now introduce our next speaker, Dr. Christine Garner, who is Assistant Vice President of Research and Assistant Professor in the Department of Pediatrics, and conducts research in the Infant Risk Center at Texas Tech University Health Sciences Center. Her research focuses on maternal and child health with nutrition within the nutrition context during pregnancy, breastfeeding, infancy, and early childhood. Today, she'll be speaking on the role and requirements of carbohydrate in pregnancy, lactation, and infancy. And we thank you, Dr. Garner, for your talk. Thank you. Is Dr. Garner on?
It would help if I unmute. Can you all hear me
there
now?
We go.
Sorry about that.
Welcome.
There's always one that does it, right? So thank you for this opportunity to join this esteemed group of presenters to discuss important issues related to carbohydrate during pregnancy, lactation, and infancy. And I will proceed in that order during my presentation. I'll discuss carbohydrate requirements and metabolism of carbohydrates that is unique to these life stages, and recent research that is relevant to revisiting the DRIs. So to set the context of carbohydrate requirements during pregnancy, let's first remember that pregnancy is a time of metabolic changes where weight gain is recommended to facilitate the best outcomes for both mother and baby. Nutrient requirements are increased during pregnancy to support maternal physiology and facilitate proper growth and development of the fetus. Here we have the weight gain recommendations that differ based on maternal pre-pregnancy BMI, such that those with the highest BMIs should gain the lowest amounts of weight during pregnancy. Notably, there were insufficient data to provide more tailored gestational weight gain guidelines for individuals with higher grades of obesity when these guidelines were created in 2009. And all of this is relevant because carbohydrate is a macronutrient, and its metabolism also differs among those with overweight and obesity, as we just heard from Dr. Gower. So in setting the DRIs for carbohydrate during pregnancy, there was recognition that pregnancy requires increased energy or fuel. Increased fuel requirement supports the mother's higher metabolic rate, establishment of the placental fetal unit, and growth and development of the fetus itself. In early pregnancy, the mother's energy stores increase, and later in pregnancy, her energy expenditure increases. Notably, the fetus does prefer glucose for energy, and it can also use ketones. So carbohydrate metabolism shifts in pregnancy to supply the fetus with adequate glucose. Pregnancy is a hyperinsulinemic state, and concentrations of insulin may double by the third trimester in a normal pregnancy. At the same time, peripheral and hepatic tissues decrease glucose uptake, and the liver increases its glucose release. Insulin resistance during pregnancy serves to shunt ingested nutrients to the fetus, thereby producing a maternal fetal glucose concentration gradient that favors glucose transfer through the placenta to the fetus. The glucose is delivered to the fetus through the placenta, where it is used by the fetal brain, as well as for fetal growth and fat accumulation. When insulin resistance is too extreme in the mother during pregnancy, this can result in gestational diabetes that result in excess transfer of glucose to the fetus and can result in overgrowth. And this condition requires management through diet modifications and often medications or insulin. So the DRIs for carbohydrate were set using the brain's requirement for glucose as the base. And the DRI during pregnancy uses the EAR for a non-pregnant female, plus the estimated glucose requirement for the fetal brain. For this estimate, the consumption of glucose in an adult brain was applied to the weight of a newborn brain and assumed that the fetal brain may also derive about 30% of its energy from ketones if there was a glucose deficit. This produced an EAR of 135 grams per day, and to set the RDA, it was 130% of the EAR. And so if one consumes the RDA of carbohydrate on a 2,000 calorie diet, which is notably low for most pregnant individuals, this translates to about 35% of energy. So what's not included in the DRI is the placenta. The placenta is a dynamic organ that prefers glucose as its dominant fuel. Recent, very sophisticated studies have utilized this technique called a 4-vessel sampling technique that is actually done during cesarean delivery. So they had 179 individuals in this study. They drew blood samples from both sides of the placenta, from the uterine vein and radial artery in the mother and the umbilical vein and artery. And they provided estimates of glucose uptake for the uteroplacental unit. And the measurements indicated that the fetus consumed about 70% of glucose and the placenta itself consumed 30%. So this translated to a calculated estimate that the placenta itself used 36 grams per day of glucose, which if accounted for in the DRIs would increase the EAR to 171 grams per day. So we have estimates of carbohydrate requirement for the maternal and fetal brain, as well as the placenta itself. And I pose the idea that a pregnant body is not simply a non-pregnant body with a placenta and a fetus, but rather there are hormonal and metabolic shifts that occur during pregnancy. Tissue stores are accrued, and there's growth in both breast tissue and the uterus. It's likely that the mother's, or at least it's possible, that the mother's body itself may require extra glucose to support these changes. And of course, questions remain surrounding, what does one really need to eat to meet weight gain recommendations and support a healthy pregnancy, particularly when we consider the broader context of an individual's BMI, which may range from 18 all the way up to 50, 60, and even 70. So before discussing data in humans, we have reason to believe that insufficient carbohydrate during pregnancy may be problematic. In mice fed a ketogenic diet, mothers had reduced fertility, a smaller litter size, and high risk of fatal ketoacidosis during lactation. Adverse fetal effects were also observed with unusual growth patterns, changes in brain structures, changes in behavior, enlarged heart, and slow growth after birth. In this figure, we see brain regions that are the colored sections that are statistically different in the embryos of mothers with a ketogenic diet compared to those with a standard diet. The blue regions indicate those that are significantly smaller with a ketogenic diet. Those are the cortex and the hippocampus. And red regions that indicate those that are significantly larger in a ketogenic diet, and that would be the hypothalamus. So on to women. There's evidence that carbohydrate intake may affect whether or not one may even get pregnant. We know that excess weight is a risk factor for infertility and that weight loss improves fertility among those women. A systematic review of 7 studies that examined effects of a diet providing less than 45% of energy as carbohydrate found that the reduced carbohydrate diet resulted in decreased circulating insulin, resumed ovulation, and improved pregnancy rates. However, it's unclear whether it was the carbohydrate restriction itself or whether it was really energy restriction that produced these effects, as nearly all of these diets were energy restricted as well. There's also minimal research on the effects of low carbohydrate among women with overweight without PCOS and the impacts on fertility. Two studies have examined the association of low carbohydrate diet with neural tube defects. Both had similar findings, so I'm showing you here the larger of the two studies. This was a case control design with data from after folic acid fortification of the food supply. And data for the 3 months prior to conception was assessed with food frequency questionnaire. And the investigators selected the bottom 5% as those with having restricted carbohydrate. And this happened to be equivalent to 95 grams per day. As you can see in the table, the restricted carbohydrate group did have lower folate intake, but there were no differences in folic acid supplementation. Also, interestingly, a larger portion of them were, of those with the carbohydrate restriction, were also intending to become pregnant. They found that the restricted carbohydrate group had a 30% higher odds of neural tube defect, and this was after adjusting for race and ethnicity, education, alcohol use, as well as folic acid supplementation, and even caloric intake. And a study that examined data prior to folic acid fortification of the food supply had some very similar findings. So next we'll take a look at infant outcomes according to maternal carbohydrate intake in pregnancy. In a large Japanese cohort, dietary intake were collected and associations with macronutrient distribution with birth weight were examined. Mean carbohydrate intake in this sample was 234 grams per day, which was about 55% of total energy intake. In this figure, we see a histogram showing the percent of energy intake from carbohydrate, and the dots indicate birth weight. A threshold for carbohydrate of 45% was identified, below which birth weight decreased as carbohydrate intake decreased, and this was also accounting for energy intake. And the authors concluded, stating that results strongly suggest that a balanced diet fulfilling minimum requirements for all macronutrients was ideal for avoiding fetal growth restriction. So there are several studies that have examined the effects of low carbohydrate intake on infant size at birth. And here I'm just summarizing some of the key findings. Lower birth weight and fat mass have been associated with low carbohydrate intake, although one study reported no association, and to add a bit of challenges, some of these studies did not report the amount of either the amount in grams or the percent of carbohydrate consumed. Two studies found that smaller head circumference was associated with lower carbohydrate intake, and luckily both of these studies even reported what that low carbohydrate intake was. Length at birth was lower with lower carbohydrate intake when comparing the bottom quartile to the top quartile. However, those carbohydrate intakes were also not reported. And so one of the biggest challenges here with these studies is that in all but two, carbohydrate intake was confounded by low energy intake, and also unfortunately carbohydrate intake was not always reported in these studies. So next we'll review carbohydrate during lactation. So during lactation, a woman's requirement for carbohydrate increases, which has been assumed to be entirely for the lactose that's produced for human milk. Lactose is secreted in human milk in relatively consistent concentrations at 74 grams per liter, which is equivalent to about 240 calories per day. Lactose is synthesized in the mammary gland from glucose, and to meet the increased need for glucose, an increased supply must be obtained from ingested carbohydrate or increased supply of amino acids to prevent utilization of the lactating woman's endogenous proteins. The carbohydrate requirement for lactating individuals is based on the EAR for non-pregnant females, plus the average amount of lactose secreted into milk daily, which is based on the average lactose concentration and the assumed daily volume of 0.78 liters per day for an estimated 60 grams per day. So the EAR is 160 grams per day. And again, a coefficient of variation is applied to get the RDA. So here are the components of carbohydrate requirement that are accounted for in the current DRIs. We have the maternal brain and we have human milk lactose, assuming that 780 milliliters per day of milk are produced. When we look at the bigger picture, we see something a bit more complicated. In the maternal body, sufficient nutrients must be available in the blood to supply the mammary gland with substrates. And the maternal body has its context of its own weight status and possibly weight loss, which is actually expected during lactation. And in human milk, we also now know that oligosaccharides are the third largest component of breast milk, as these are found in quantities even higher than protein. There's also a small amount of glucose in human milk. And finally, the volume of human milk produced will change the amount of carbohydrate required. Many women, as we know, do not breastfeed exclusively. So let's take a closer look at the carbohydrate components of human milk. Producing human milk requires substantial carbohydrate substrate. Lactose has already been covered pretty well, and as long as a woman is exclusively breastfeeding, this may be a relatively good estimate. Oligosaccharides, which are composed of 3 or more saccharide molecules, are estimated to be secreted into human milk at between 1 and 1.5 grams per deciliter. And so when we take this times the assumed daily volume of milk production, this translates to an increased need by 8 to 12 grams per day. And although oligosaccharides are not digestible to the infant, they do serve as a fuel for healthy gut bacteria and have been shown to be important for infant health. Glucose and fructose are present in very small amounts in human milk and likely do not impact maternal carbohydrate requirements. So a few studies have examined modification of carbohydrate intake during lactation. And so lactation ketoacidosis is a rare condition, but it's still notable as it demonstrates the importance of having adequate carbohydrate intake and substrate available during lactation. There have been 18 case reports in 19 patients in the past 40 years. And patients typically present to the ER with nausea, vomiting, malaise, abdominal pain, and/or difficulty breathing. And in all of these cases, ketonemia and ketonuria were present with an anion gap metabolic acidosis. Precipitating factors of this condition were all related to substantial decreased carbohydrate or total intake, most of which were related to dieting. Those were low carbohydrate diet, high protein, ketogenic, or simply a very low calorie diet. And importantly, in all of these cases, full recovery was achieved with a combination of IV dextrose and also consuming a carbohydrate rich or a balanced diet. One study investigated whether non-lactose carbohydrate in human milk could be modified by the diet. And to do this, they provided a high fructose corn syrup sweetened beverage to lactating mothers and measured their milk content for 6 hours. They found that fructose increased with consumption of the sweetened beverage for a full 5 hours after ingestion, as is shown in this figure. Although the fructose was present in very small quantities, it was clear that fructose consumption and concentration in milk are linked. We do not know what the metabolic effect in the infant might be in response to this. So next I'll discuss carbohydrate needs during infancy. I was charged with the task to address only the nutrients that are actually absorbed and used by the human body. So although oligosaccharides are important for the baby's health, they will not be covered in this portion. The 2005 DRI stated that the lower limit for dietary carbohydrate compatible with life for optimal human health or for optimal health in infants is unknown. Thus, human milk, being the optimal source for infant nutrition, was used to set the carbohydrate requirements. And lactose is the primary human milk carbohydrate. So carbohydrate DRIs for infants 0 to 6 months of age were based on lactose content of human milk and thus set at 60 grams per day. And for infants 7 to 12 months of age, a lower amount of human milk was assumed. And the remainder was based on the median carbohydrate intake from complementary foods from the NHANES 3, which was 51 grams. We do know that many complementary foods being fed to infants in the US are high in carbohydrate, and they may or may not be optimal. While we would love for all babies to be breastfed, many and really most infants in the US are not exclusively breastfed. And so I did want to briefly address carbohydrate intake and formula. Many infant formulas do provide carbohydrate as lactose, but many also provide corn-based sugars, which they typically tout as being easier to digest. And so here I'm showing you data from a randomized controlled trial of formula-fed infants who received a lactose formula in red or one with corn syrup solids in blue. They also provided a breastfed comparison group, which you see in green. Infants fed the corn syrup solid formula had lower ketones in the top two panels, which the investigator suggested may have a negative impact on infant development. These infants also had significantly higher insulin in the bottom right panel than breastfed infants, and the lowest average glucose. Metabolic differences were apparent between these groups, and the long-term impact should probably be investigated. So challenges exist in interpretation of the studies published to date. In studies examining outcomes of pregnant mothers consuming various levels of carbohydrate, maternal glucose concentrations are often not reported, and thus the maternal fetal glucose concentration gradient is really unknown. Estimation of carbohydrate intake has challenges, particularly when estimating from food frequency questionnaires, and dietary intake is typically self-reported. The definitions of low carbohydrate and carbohydrate restriction, as we've heard from others, these can vary substantially from as low as 95 grams per day or as high as 185 grams per day from the data that I've shared with you. And they may or may not even be reported at all. Carbohydrate intake is often confounded by total energy intake, which is not only frequently not accounted for, but also frequently unreported. And finally, any change in carbohydrate automatically results in changes in the percent of energy from fat or protein, which may also impact outcomes. We do know that extreme protein intake at either end of the spectrum is associated with low birth weight, and high fat intake during pregnancy is also associated with increased adiposity in the newborn. So much remains to be known. And in interest of time, I'm going to move on to the summary. So carbohydrate during pregnancy is important for normal fetal growth and development, and the placenta requirements for carbohydrate should probably be accounted for. Carbohydrate needs for conception and pregnancy may differ by BMI status. And carbohydrate requirements are high for production of human milk, although not all of the carbohydrate in human milk is currently accounted for in the DRIs. Exclusively breastfed infants have the best outcomes, and relatively little is known about carbohydrate from infant formulas that are not lactose, or the carbohydrate that should be consumed from complementary foods. And carbohydrate intake in the context of other macronutrients should be examined, which kind of falls along the lines of what we've seen in the chat today. So with that, I'm happy to take questions.
Thank you so much, Dr. Garner. That was fascinating and very helpful, both in the context of what the 2020 DGAC was able to recognize as an important factor, which is lots to learn about exactly how best to identify and perhaps make more precise dietary recommendations during pregnancy based on things such as BMI, which, you know, as we know, approximately 60% of pregnant women are preconception overweight or obese. So the points you're making are very relevant at this time. I'm looking to Dr. Erdman to see, do we have time for questions or should we move forward?
I think we have time for a few questions, yes, and then we'll have a quick break before the panel.
Okay, and due to what Cy said with Dr. Gower, I don't know if we're doing both or just.
No, I think we'll just stick with the last talk and then we can catch up later. And I see Chris.
Okay, oh, sure, Chris.
You know, I just had this question in the chat about these milk oligosaccharides. You know, I'm not saying that we're going to do that, but if we're going to do DRIs for dietary fiber, you know, where would these milk oligosaccharides be? Would they be with the carbohydrate DRIs, or would they be with the where we do soluble and insoluble fiber? Given that they cannot be, you know, should we decide that the fiber is, you know, some kind of carbohydrates that can't be utilized by metabolized directly by the host, or like a gnotobiotic host?
Yeah, that's a good question. I find that it's difficult to separate everything out because the reality is that diets are consumed as a whole. We don't consume individual nutrients at a time. And so,
right, but people are starting to add these
question.
things. People are starting to add these things to foods. So the HMOs, as you know, individually, I mean, humans make about 200 of these HMOs, and each mom only makes about, you know, in the 30 to 35 or so. But, you know, some companies are deciding I'm going to add FOS or GOS or whatever to the formula to make it look more like, you know, human milk. And, you know, so, yeah.
Yeah, I think, I'm not sure what exactly the question is there, but I mean, ideally, all infants would be consuming human milk.
Yeah, that's right.
Which has lots of human milk oligosaccharides in it, with more than 200 have been identified to date. And yes, I believe there are 2 or 3 oligosaccharides that are currently being added to infant formulas. Only one of which is actually one that's present in human milk. I believe it's 2-fucosylactose. And they're potentially beneficial in infant formula. As far as who addresses whether or who addresses these in the DRIs, I guess that's all up to you.
Dr. Beer, did you want to add something?
Well, you know, I just wanted to go back to earlier this morning when we talked about using words like requirements for stuff you can make inside the body. And Chris and others have pointed out the complications of dealing with this. And the same really applies to fiber and HMOs. I mean, should we have requirements for stuff that never actually enters the body? Okay, so how do we deal with that? These are not so simple questions, and they're, in my mind, absolutely subjective because the data required to know that they're, you know, any good, we don't have.
Yeah,
by the way, I just to pursue that slightly, those of you who know me know that I've talked repeatedly about the days when we fed infants evaporated milk formula, including me, for example. I could be really tall and really smart and really successful if I were breastfed, but I wasn't. I got evaporated milk formula, which has none of these things in it at all. And there's absolutely nothing that anybody can measure in a child over the age of 5 or 6 or 8 that tells anyone whether they were breastfed, formula, human milk fortified, you know, imitated formula, or evaporated milk formula. By the way, not outside of the developing world where infection and things may take place.
We do have, I mean, we do though know that, you know, moms who can't fucosylate their oligosaccharides are more susceptible to infectious diarrheas, their infants.
Well, we you know, I mean, we can, you know, I know this is a complex subject. It takes too long to discuss, but we know that there are exceptions to all of these kinds of things, and there are human diseases that result from various, you know, genetic deficiencies and stuff, and that sort of leads me around to the really unanswerable question is, and John brought this up in the introduction, is how do we define what's the normal population state that we're going to use to make these definitions, right? And when you come to metabolic fuels, it makes a lot of difference whether you're talking about postprandial, post-absorptive, and slightly fed, you know, energy sufficient, energy deficient, blah, blah, blah. So, you know, this eventually comes down to a bunch of intelligent human beings, wherever they are, coming together and deciding what's the best default position that, you know, that's acceptable for most circumstances, but it's not an absolute. We don't know the absolute.
Thanks.
All right. Other questions for Dr. Garner? I have a feeling others will pop up as we get to the bigger panel. And do we want Dr. Gower now, or
Why don't we take our break right now and then come back at 20 after the hour, depending on where you're living at the moment. And then we'll have quite a bit of time for panel discussion, and particularly we can catch up with Dr. Gower's talk because we didn't have time there. So why don't we take our break until 20 after, and I'll reconvene at that point. Thank you. speakers to be available for questions. I want to take this time to thank each of the speakers. I know that you spent quite a bit of time on your presentations. This is not something that you have locked away somewhere and pulled off the shelf. I know you started this from scratch, and really appreciate the work that you put into this. These have been some really great talks, and I'm expecting a lively discussion during Q&A. Since we didn't have time for Dr. Gower's questions for her talk, I suggest we go ahead and start there. Are there questions specifically for Dr. Gower, and then we'll move on to general discussion. So I'll just start. In end of your presentation, Barbara, you mentioned there should be as far as dietary recommendations, it should be a tolerance versus a requirement. So that's a strong statement. And it seems like most of your presentation was focused on people who either had insulin resistance or metabolic syndrome or fatty liver disease, et cetera, rather than the general population. So in the terms of the general healthy population, would you continue to use the word tolerance?
Well, I guess I do human research studies, and it's an open question now, is what is the general population? What I can tell you is most people who join our research studies, I mean, we do get lean, healthy individuals, but we also get a lot of people who are overweight, who have obesity, who have some degree of metabolic disease. So, you know, this has come up earlier today also, is who is the, you know, the population today? But what I also said on my closing slide was that I think it depends a lot on the individual, on your metabolic health status, your physical activity level, and so forth and so forth. Carbohydrates are incredibly beneficial. They're a great fuel. And if you're healthy and active, you're going to want to consume some. But I still think there's a difference between heavily processed grain foods and fruits and vegetables. And that's what it comes down to, really. I'm not saying don't eat carbs, but what I am saying is, once you have type 2 diabetes, some of our patients can tolerate small amounts of carbs. Some of them can't. There's a tremendous amount of variability. I mean, once you've crossed over to that having diabetes, your metabolism is different. I don't know if you can ever go back. And there's a huge chunk of the population is at risk for type 2 diabetes. Family history is one of the biggest risk factors for type 2 diabetes. There's genetic components. So if you're someone who has that, I think this is a different metabolic situation than someone who doesn't have that baggage. So these are tricky questions. I do think that we have to take the heavily processed grains. I mean, that's, to me, we can't even talk about carbohydrates without differentiating grains from fruits and vegetables. Because I don't know that there's any requirement on anybody's. Does anybody really need heavily processed grain-based snack foods? That's a different question than does anybody need carbohydrates? So it's hard to answer. And again, it's not one size fits all. There's tremendous variability in what people need or can tolerate. So that's not an easy question to answer either. It depends a lot, like I say, on your genetic background, on your metabolic health, on your physical activity level, and so forth.
Thank you, Dr. Beer.
Well, I guess I'm unmuted. You know, there have been, you know, this vast number of important questions that have arisen this morning about, and they really highlight the difficulty of doing studies with diets, isolating the culprit, so to speak, how to deal with the fact that you can't maintain energy balance if you take something out without putting something else in, and all of these sorts of things. And I guess, and what the ground state is, which I mentioned earlier. So the first thing is, I think over the course of evolution, Mother Nature made it possible to deal with any diet that was thrown at the human being. And they have to deal somewhat differently because you don't have to deal with carbohydrate if you don't have carbohydrate in the diet, blah, blah, blah. But the ability of the human being to respond to vast differences in dietary composition is, really, I think, the norm rather than the outlier. Barbara talked a lot about stuff which I firmly believe in. I want to also mention that even though, I talked about the brain, remember back in the 60s, there were people who actually measured the disposal of fatty acids across the liver with catheterization studies in which they were able to partition the fate of fatty acids delivered to the liver into oxidation, reesterification to TGFA or ketone body production, blah, blah, blah. So, back in the old days, there were, these kind of experiments were in fact done. The other thing, which I think is really important, and Barbara discussed it really, is, whether we're talking about energy, isoenergetic states, or excess or deficient energy. And, there is no question that there's a vast difference in what happens depending upon whether the body is presented with more energy than it needs or less energy than it needs. And I would argue that if you take every adult and put them in a room and lock them up and give them 1,200 calories, irrespective of the composition of the calories, they will lose weight. Okay, now in the context of high fat and high carbohydrate diets and stuff, we have a vast body of literature. Most of it was summarized, but it has some problems with it. The first is that, to me, is that most of the differences in weight loss and what happens in those diets are what happens in the first few months, 6 months, even a year. By year 2, there are a lot of studies which show that the weight at the end of that time is pretty much the same, irrespective of composition. So to get a weight loss and the effects, you need to have first an energy deficit, and secondly, you have to keep it long enough to see the effect. And many of the studies that deal with changes in dietary composition deal with following people in an outpatient setting. I mean, there are a few that measure double labeled water and things like that, but most of them are in an outpatient setting. And frankly, we don't know, I don't know anyway, but maybe it's me, I don't know whether this is simply an issue of slight differences in compliance. That is, the hedonic benefits, for example, of a low carb diet may allow people to have 10% more compliance. And the results are really not due to the carbohydrate at all. They're due to the fact that there's an energy deficit that's better kept for longer, et cetera, et cetera. And, we're in the middle of a, sort of very complicated things. But I think that we really, if you're going to define whatever the normal ground state is, I think it has to be defined in the context of isoenergetic, okay, and some estimate of what normal weight is. Now, we have definitions now which say that people who are at the 85th percentile for BMI are at risk for obesity, blah, blah, blah. Does that mean people who are below the 15th percentile for height are at risk for shortness? We're mixing populations here. We've decided that we're going to accept the definitions of normal weight back for the BMI charts that existed 50 or 70, 60 years ago. And I don't know that, that we've really solved all those issues. I'm less, certain about those than some other people.
Thank you. Dr. Esselstyn there?
Thanks. I'll start with Dr. Gower, but I am interested in the thoughts of the other panel members as well. First of all, I think not unexpectedly, we've been hearing today that there's probably no true requirement in the strict sort of traditional sense of requirement for carbohydrates. And we're really looking at an indicator that's more of, a functional or beneficial outcome, that's associated with good health. And in the construct of the DRIs, we have sort of a separate set of values that are related to reducing risk of chronic disease. So I think some of the things we've been hearing about are, avoidance of ketones or preferring glucose as an energy source. We've been hearing about potentially considering nutrient density of the diet as, a beneficial or functional outcome, maybe more complete consideration of needs during pregnancy and lactation. But Dr. Gower, where I'm struggling a little bit is a lot of the stuff you presented is on metabolic indicators, and there's a lot of crossover with chronic disease. And I'm wondering if in your mind, there's a way to separate out how we might be able to look at it in terms of more of a requirement type of value as opposed to reducing risk of chronic disease, and your thoughts on that, and then thoughts from other panel members as well.
Well, I guess it kind of goes back to what I said a minute ago. I think carbohydrates are an excellent fuel. So, if there's no question about that, particularly for people who are physically active. I still don't know if that's it. I get hung up on the word requirement because I know there are athletes who actually utilize a ketogenic diet and claim to do just fine. So that would argue that there is no requirement. But then you'll talk to people who, and this is all anecdotal, unfortunately, that are athletic, that obviously benefit from eating carbohydrates. I think the short answer is, if you really want to ask about a requirement, no, it's not required. Fat's a perfectly fine fuel. What humans need is fuel, and you can get what you need from fat. Now, I'm not talking about infants and pregnant women. I think those are special cases. But if you're talking about a healthy adult, they can probably get obviously we need some protein. And then in terms of a fuel, you can probably get most of what you need from fat. Do we need carbs? No. But that's a separate issue, is, are there benefits of eating carbs? Which there are. They're a very easily accessed fuel. They do provide a great deal of energy. And as David presented, there's a lot of nutrients that come along with eating carbohydrates. But that's a completely different question, I think.
Others on the panel? David.
Sorry, I might add to Krista's question. We have more than one metric for the macronutrient DRIs. There's what was set as an estimated average requirement, but then there's the AMDR. And Dr. Lichtenstein talked just briefly about that. And that's, when I was with the federal government, I was co-chair of the DRI steering committee for a lot of years. And this almost kept me up at night, that the AMDR is 45 to 65% of energy. But we know that there are diets that go up to 75% of energy in traditional Southeast Asian countries that are perfectly compatible with better metabolic health than most Americans exhibit. And we know that the lower limit is, we don't know what the lower limit is, but we can extrapolate it's probably in the neighborhood of 15%, 20% carbohydrate. We don't have any good, solid, long-term data on this. But from a lot of the short-term studies, I think we can extrapolate that the AMDR is truly a lot wider than it was. And I'm wondering, Alice, can you talk freely about how the AMDR came to be 45 to 65?
Well, I alluded to it earlier today. It was a stopgap measure. We were asked to come up with RDAs for fat, carbohydrate, and protein. And the committee felt that within the definition of the time of essential nutrients, there was no way we could do it, because one of the things that one needs to do initially when establishing an EAR, that ultimately is going to be the RDA, is that you have to have an outcome variable, and you have to decide at which outcome variable. So it was really a bidding game of, oh, well, I saw this study that had, this, and people did fine, and somebody else that. And unfortunately, that's what happened. And I was just as much a part of it as anyone else. But I think it's because we didn't have the opportunity to really think through it. And I will say the same situation came up with cholesterol, which is not essential, and trans fatty acids, which there was a lot of pressure to come up with an EAR and RDA because it was necessary for the nutrient facts label. And that was one thing that we absolutely couldn't. But as far as the acceptable macronutrient distribution range, it's a possibility that maybe it actually is retired, because now we have the chronic disease risk reduction, and that in a sense came from the sodium potassium DRI committee, because again, we were challenged with what do you do in a situation where you have unique nutrients. In this case, we always think of the DRIs as for essential nutrients. Certainly sodium and potassium are essential, but that's not what the public health issue is. So I'll leave it at that.
Let me leave you on the hot seat for just 1 second more. In the constraints of the 3 macronutrients interacting, didn't you limit the total amount of dietary fat? And that's one of the reasons why carbohydrate had to be higher?
Wait, what's the question about dietary fat?
You didn't want dietary fat to be too high. That's why carbohydrate had to be higher than some of us might have set it at.
I don't specifically remember that. I literally remember it more as this bidding. Oh, I found this study, I found this study. But I think we also have to remember in the mid and late 90s when this work was going on, we were at the height of the low-fat diet craze and dealing with the unanticipated consequence that it wasn't going to be what we had envisioned as far as a low-carb diet, but it was going to be non-fat ice cream and brownies and cookies and those kinds of things. So there was also this concern about saturated fat, but at least we've separated that. It's not the amount of fat, it's the profile of the fat.
I will point out that there are a couple of groups doing scoping reviews on total carbohydrates and dietary fiber for this process. If the steering, I assume the oversight committee knows that, but just in case, that should be on your radar.
I think a fundamental question is, can you consider fat, carbohydrate, and protein in isolation? Because when one goes up, another has to go down. We know that we just don't take things out of the diet. People are going to replace. So the issue is we're going to need, I think we're going to need some very complex models on what happens when there are slight differences in all 3. And again, also in terms of what the impact is going to be on the micronutrient intake.
Good point. Dr. Bear, was your hand up there?
Yeah. First I'd like to follow up on Dave's, comment about, how low is a low carbohydrate diet, blah, blah, blah. So, the numbers that I showed about brain glucose utilization are give or take 100 grams from age 6 forever. And that's a 20% carbohydrate diet on a 2,000 calorie diet. Nobody keeps those diets. That's below any level of what we're talking about as low carbohydrate. We on a so-called quote unquote most low carbohydrate diets, we're satisfying that number. Okay, so do with it what you will. Take a little away, add a little more, but it's the kind of diets that nobody keeps for a long, or by the way, no one except the really committed keep for a long period of time, you know, blah, blah, blah. And the other thing I just want to interject is, you know, and I presented very hard short-term data. Barbara presented another set of hard measured short-term data. All the data that deal with does this matter in the long term, almost all of it are observational studies which cannot prove causality, which can't measure food intake, which don't deal with food composition and cultivar and storage differences, and which, you know, have 50 unknown unknowns, covariates associated with them. So that's fine, okay, but those are all model and, you know, assumption dependent conclusions.
Let's see, Dr. Davis and then Dr. Lichtenstein.
So I want to actually follow up on Alice's comment and pretty much having to look at the macronutrient distribution. And we actually had this conversation in the chat privately, but it's more putting into context, again, why we're here. You have to look at the macronutrient distribution and what's substituting for what when you're thinking about chronic disease risk reduction. The reason we're having this meeting today is to say, is there an absolute requirement for carbohydrates? That's pretty much the question that we're asking. It's not the question of are there benefits of a low carbohydrate diet, which we will be looking in terms of chronic disease risk reduction, but is there an absolute requirement just for carbohydrates? Similarly, that when we're looking at the requirements for essential amino acids or essential fatty acids, it will be for those specific nutrients.
So before we move to Alice, you know, you could ask that question, but then based on the last presentation, by what population? It appears as if at least some of our subpopulations, there is a clear absolute requirement. Maybe your question is there absolute requirement for adults? So, Alice?
Well,
Actually, can I say one? Sorry.
Yeah, go ahead,
To cut you
Susan.
off, Alice. And we're not asking, is there an absolute requirement? We're asking, are there biomarkers that should be utilized or be thought of to actually look to provide evidence? It's not for us to say, it's not for this group to say, is there a requirement? It's just for this committee to say, are there biomarkers or endpoints that we might not have been considering that would be worth looking at what literature is out there going forward prior to the committee meeting to actually look at the literature and say, what does it mean?
Thanks.
And actually, one of the points I was going to make has to do with that. For essential amino acids, there are biomarkers and there are clinical manifestations. For essential fatty acids, there are biomarkers and there are clinical manifestations. The question is that for carbohydrate as well? The other point I wanted to make is when we talk about carbohydrate, fat, and protein in the macronutrient distribution, we are going to have to also address the issue of quality. And that comes up with the fiber, it comes up with protein, and it's going to come up with fat also. So I just think by recognizing the complexity of the situation, probably in the long run, it'll help address it or come up with a mechanism for addressing it.
Dr. Beer?
Well, I just, you know, Alice just said pretty much what, you know, I was going to say is if we say there are requirements for essential fatty acids and for amino acids, we need to apply the same type of criteria to carbohydrate. Are there physiologic measurable biomarkers and are there consequences? Okay, and then you get into the complicated issue of, how much of a consequence is a consequence. So we have a variety of amino acids that are conditionally essential in renal disease and in the newborn and in stuff like this. So I think, John, you wrote a thing about the last DRIs. I can't remember exactly what it was called, but it dealt with applying different criteria to coming to the number. And I think that this is probably the job of the new committees, which is to say, we need to treat all of these things the same. So we need to answer some very fundamental generic questions that we apply to all the nutrients. And here we have complications. So let's use Ali Owen's 40-day fasted study. These people were, alive, talking, and all that sort of stuff, but their metabolic state was different. Now, is that better or worse? I don't know.
Thanks, Dr. Gardner.
I'll unmute myself first this time. So I feel like pregnant or lactating individuals may be sometimes viewed as subpopulations, but the reality is that that's transient. They're only pregnant for 9 months. They're only lactating for, recommended, ideally 2 years after each pregnancy. And so if there's so I feel like there's pretty good evidence about the importance of this idea of balance between the macronutrients during those life stages. And if there's no requirement aside from those life stages, how do we expect them to change their diets for these life stages, when they become pregnant or while they're lactating? How would we expect that to occur? And I realize that that's outside of the idea of, this requirement for carbohydrate, but I still think it's relevant practically speaking.
Other factor too is, women may not know they're going to become or are pregnant for a while, and therefore, they would fall into the category of potentially getting pregnant.
Exactly. Many pregnancies are unplanned.
Danny?
Well, I just want to, Christine emphasized really with lactation, the same thing I was talking about. There's a net loss of carbon. Okay, so if you want to replace it, you need to get the carbon from somewhere. That's the lactating state. In the pregnancy state, remember the fetus is 3.5 kilos, 5% of the body weight of most mothers, and even less than 5% of the body weight of most of today's mothers. And for the first half of gestation, there's hardly any change, right? It's all in the last trimester or bulk of it. So the net loss of carbon into the fetus and the pregnancy state is relatively minor there compared to lactation, where it's a lot going out. So the considerations are really different.
Thank you. Others, it's your chance to ask questions, bring up other issues. So Dr. Davis was asking for biomarkers for carbohydrate requirement. What does the group think about that? David?
Yeah, the obvious one is ketones. I think it was, Barbara, I don't remember who said, we have ketones circulating all the time. We make them all the time, and we have extensive data on, post-absorptive, levels of beta-hydroxybutyrate and acetoacetate. They've been measured thousands and thousands of times over the last 50 years. And that's some basal post-absorptive state. Then somewhere they start to go up. And I would argue that's one, sign that there's a switch in metabolic fate, of fatty acids and other fuels. And the other point that Barbara made is insulin. I mean, there's no question that there's a vast difference between no insulin, a touch of insulin, and a normal circulating insulin level on the disposal of all three major metabolic fuels. So, I don't know. It depends again on whether you decide that a circulating ketonemia of 1 millimolar, which you might get after an overnight fast, or, usually a bit lower, but okay, whether that's normal adaptation or something abnormal. I don't know that we have the answer to that.
So,
Dave.
thank you. I think there are two questions that are somewhat related, but also distinct. One, is there a metabolic response, and is there a physiological response? And the physiological response is dietary fiber is really probably the only truly essential form of carbohydrate we need. And the physiological response to a deficiency is constipation. And the over-the-counter pharmaceutical industry is thrilled that we don't eat enough fiber because they're selling us billions of dollars a year in laxatives. And you can say it doesn't get metabolized, it doesn't get into the body, but it's performing an essential physiological function in the colon. And you don't get fiber from non-carbohydrate foods. And the current DRI views it as a bioactive, not as an essential. And I think that's problematic.
Thank you. Nadine.
Thank you. I was wondering about the protein aspect of things. Like some studies show that there was by decreasing carbohydrate intake or too low maybe, that there was an impact on the use of protein. And other studies shown by Dr. Gower, if I'm interpreting correctly, was that the protein has remained intact in some of the studies that were done. And so I am wondering if it has to do with the percent of carbohydrate, and if there is a biomarker with protein that can be measured that could also be looked at.
Their response to that?
What I probably said was that in most diet intervention studies, protein is left at 15 to 20% because that seems to be protein is fairly invariant in the American diet or the human diet. As far as percent, I tend not to think about it percent carbohydrates. I think about more like grams. I just feel it's easier to wrap my head around what people are actually using in terms of a gram amount, because percentages will change as people eat more or less. About the biomarker piece of it, I cannot think of a circulating, almost any kind of biomarker for carbohydrate deficiency. This is what I've been sitting here thinking about. Is there any way we can identify carbohydrate deficiency? And I just draw a blank. I don't think there is one, but it seems like what we're constantly identifying is carbohydrate excess or fuel excess, which almost by definition is carbohydrate excess because people don't overeat. They don't overeat non-carbohydrate foods. They just don't. So overeating is overeating carbs, and we have lots of biomarkers for those. Like Denny just said, we have, insulin's a good one. High levels of insulin and high levels of glucose are never good. That much we know. It is never good to be hyperglycemic, and hyperinsulinemia is bad for many reasons. That we can identify, but on the other end, there doesn't seem to be anything. I can't think of, when you don't eat carbs, it's not like your glucose drops. That doesn't happen. Your glucose stays normal because your liver's always making glucose. So I can't think of a good biomarker for a low carbohydrate intake.
Well, by the way, I hadn't really been thinking about this, but, we first of all always think of insulin as the glucose controlling hormone, which it is, for no question. But we have a whole bunch of very carefully done insulin clamp studies looking at insulin's effect on proteolysis and on lipolysis, both of which are far more sensitive than insulin's effect on carbohydrate. And, if we want to use, indicators of when there's enough insulin or not enough, I mean, those are extremely sensitive consequences of a change in insulin level. And then we're talking about protein. And remember, we have a vast number of studies on nitrogen balance, different levels of protein. I mean, huge. And just in the normal population, but remember the chronic renal failure people did a huge number of studies. And what we know is Americans eat far more protein than they ever need, that if you get to levels of 0.6 of a gram per kilo per day, you can maintain balance, but at a cost. So we bump that up a little bit. Even the real renal disease folks in the days of, reducing protein intake as much as they could, backed off a bit. So we get back into levels, let's say 0.8 grams per kilo per day is requirement, but that you get there by adapting other things, right? It's not that things don't change. They do change, but we can survive that. And we're kind of in the same, place here with carbohydrate and with dietary fat, It's deciding the difference between, adaptation, which one can argue is necessary as you change macronutrient intake. If you increase carbohydrate intake, you have to change, the RQ and blah, blah, blah. Because you have to burn it. And the difference between adaptation and accommodation, which you can argue is a cost of some sort. And I don't know that we have easy ways of knowing that.
So I think next is Alice.
So I actually was going to say what Dr. Gower said, that I can't think of a biomarker for carbohydrate intake. And when insulin was on the table, I'd be very reluctant for that, because we have some people are insulin resistant, some people aren't. So the different levels of insulin, different people could mean different things as far as carbohydrate metabolism. Now, whether, as Dr. Baer just brought up, that there may be some metabolic markers that are affected in fat and protein metabolism, perhaps, but I'd be concerned that they would be specific enough to carbohydrate. So
Thank you.
that's where I am.
Again, about more than 50 years ago, Jerry Reven published the levels of, insulin resistance in lean people. And it's a range like this, right?
Yeah.
I mean, there are lean people who are extremely insulin sensitive, and there are lean people who are insulin resistant. That's before we get into getting obese, right? I mean, there's a range, there's a huge range, or a significant range.
So one of the questions that sponsors wanted us to particularly address was the considerations of low carbohydrates related to race, ethnicity. And Dr. Gower did begin that discussion and presented some of her own data for this. Are there any other comments, thoughts, or is there any non-known literature on this topic?
There's just not a lot of literature on this topic, unfortunately. I think it's a huge gap. It's something we need to address. And I think it's a sensitive issue because it implies that it's not one size fits all. But I think we would be naive in thinking that it's one size fits all. I mean, genetically, we're all different. Just like Denny said, if you look at normal, healthy lean humans, there's a huge range of insulin resistance. And it's like this with everything. There's a lot of genetic variability. So I think across the board, regardless of race or ethnicity, there's tremendous variability in what diet is going to be optimal for whom, which makes it very tricky to come up with dietary guidelines. But then it also comes to the issue of energy balance. I think we have a lot more latitude. If people are eating in an energy balance situation, there's probably a lot more latitude in what they can eat. I think when things get tricky is when people overeat, then certain diets have adverse metabolic consequences more so than other diets. But then I think the question comes into, why do people overeat? And that's a whole nother, conversation for another day. But I think there are physiologic metabolic reasons that underlie excessive food consumption. So I think we just need to be sensitive to the fact that we're all different. If I go around and poke someone in the vein and collect some blood and measure glucose, insulin, ketones, glucagon, you're going to get tremendous variability. So why would those people all respond the same to eating the same food? Well, they won't. So I think this is just kind of part of a broader question. It does have ethnic and racial implications, but only as far as we have ancestral lineages that have certain metabolic traits that have tracked with ancestry over time. We're still not admixed enough that we're just one homogeneous gene pool. We're not there. We probably never will be. And so certain traits have tracked with ancestry, just like I showed the PNPLA3 polymorphism in Hispanics. It's just very prevalent. It's just that Blacks from Africa have a higher prevalence of the malaria protective gene for obvious reasons. Those types of things are still out there, and some of them affect metabolism and the response to food. So I guess I would just say it's never going to be one size, not in our lifetime anyway. It won't be one size fits all. And this is a great time for precision nutrition, is understanding how it is that different individuals respond to diet.
Thanks.
Well, some years ago, maybe 5 or 8 now, Johnny Anitas, and I think it may have been Chirag Patel, I don't know, but John wrote this brief piece, and I think pretty sure it was JAMA, which was, can we define normal anymore, dealing with the fact that everyone has polymorphisms and different, gene variants and almost everything. So where do we get normal anymore? And somebody may want to fit that into this discussion here.
Alice, is your hand still up?
Yes, it is. Well, I just wanted to give another example about genetic variability, and there's a fair number of studies that were conducted in India where there's a high prevalence of diabetes in lean individuals, and that sort of is an example where there likely is a genetic component to it. So I think it will be helpful to do comparisons in terms of that.
Yeah, I would like to echo Barbara's, remark about we don't have the data. I mean, I was part of a lot of those studies that I mentioned and worked with the people, and no one paid any real attention to men or women or, black or green or yellow or any, I mean, you had subjects. It's very hard to get volunteers, and you took them where they came from, but there was no systematic approach to this.
I mean, one thing that we should remember is that the committee has spent a lot of time talking about healthy, and that's probably not the word that we can use for the US population. And I think Dr. Erkman brought that up at the beginning, but that is definitely a challenge.
All right, other questions, other topics? Yes, Krista.
It's not even really a question, but following up on the discussion we've just been having around biomarkers and other measures, I think even more broadly, do any of the panel members see a need for any systematic reviews or other evidence preparation prior to tasking a DRI committee with looking at requirements for carbohydrate? Or is the evidence so scattered that really that's not something that needs to be undertaken at this point?
And I just want to clarify Krista's question. We are not talking about dietary fiber in that question. Dietary fiber we're handling separately.
Thanks.
All right, questions on the table?
Well, I would say it really depends on the nature of the question you ask. And earlier I made comments about applying the same rules to essentiality as we applied for fatty acids and amino acids. Well, I think that could be formulated to a question that said, do we need a systematic review to see whether or not we're treating carbohydrates the same? Something like this. I mean, you would have to really frame the question in a very specific way. I mean, I think so far we've talked in a lot of generalities. I mean,
Valerie?
Just to, I guess, follow up on what Denny just said, Krista, I'm not sure that the question is whether there needs to be a systematic review. It feels to me like a lot of the conversation this morning has been about the conceptualization of this notion of requirements for carbohydrate. And I don't think the answer to the conceptual question, which seems to be overriding here, I don't think that answer rests in a review of evidence for anything so much as it does about the framing of the question. And I don't know what the conceptual issue means in terms of the terrain that we're on with respect to the development of, or the revision of DRIs, but I feel like the carbohydrate issue puts that front and center.
Nadine?
Yes, Dr. Clurford mentioned some scoping reviews that were being done, and I was just wondering if he knew what were the questions that were being addressed in those.
yeah, I actually agree with the assessment that we need to solve a couple of very fundamental conceptual issues first. And their solution, whatever that is, should generate whether or not I'm not involved in this, I'm just a kibitzer here, but that they should generate some questions to see whether or not the references or whatever they are applied equally across nutrients, across metabolic fuels, blah, blah, blah. I don't know. I mean, but I do think it's time to rethink what we're talking about with regard to populations and things of this sort. I mean, and I realize how hard that is. I don't think there are any hard answers, but you know.
Perhaps we need to think of carbohydrate the way we address sodium, that it's not a minimum, it's a maximum.
We're still, I was going to say, yeah, but throw it in with sodium. We still haven't solved that one, you know. Okay.
No, I just mean that as far as a chronic disease risk reduction.
Oh, I'm joking, Alice. I'm joking with you. I mean, it's,
okay.
The one thing we can get no one to agree on for at least 50 or more years is sodium.
Sodium, yeah.
Right,
So,
and
no.
I don't want to speak out of turn, but Alice, I think actually maybe that is a good example where sodium, the true requirement is probably much lower than what, people are actually consuming, which is, could be said the same for carbohydrate. If there was indeed a requirement, it may be way lower than what would be considered, healthy component of the diet and what kind of foods are there. And so I think, where there wasn't a requirement value set for sodium, but there was an AI, like that quasi requirement type of value set. And I think this is, somewhat of a similar situation where we need to think of, it's not a traditional requirement, but there's got to be some kind of indicator that can be used to sort of look at, like, what would that amount be? That's not associated with chronic disease necessarily, as was the case for sodium. That was dealt through with the CDRR values. And I think that may be the same case here as well. But is there another kind of sort of functional, beneficial amount of carbohydrate that one would expect to see and perhaps advise that be included in the diet?
I was just joking because an awful lot of very good brains have been, working on the sodium issue. I mean, and We're not talking about dumb people here. We're talking about very smart people. And, you know, we have great difficulty agreeing, is there a lower limit? You know, does the detrimental effects if you go below a certain limit, and what's it, you know, and man, it's, you know, here we are, as I said, 50, 60, 70 years in, and we're still having fundamentally the same kind of argument. The answers are not easy to come by.
Cindy, did you have your hand up before?
Krista pretty much made the comments that I was planning on making. And just reiterating that we are looking at chronic disease risk reduction in terms of digestible carbohydrates and in terms of dietary fiber separate from this. We're just trying to see, is there something we're missing or something that needs to be considered just in terms of carbohydrate requirements?
Yeah, thank you. Sai?
Yeah, and I wanted to sort of add to that point about, you know, is there a lower limit? Cindy asked, is there a minimum requirement? And so maybe in keeping with Alice's comment about sodium, which was followed up, I think maybe the way to look at it now is that, you know, maybe we should look at the evidence that is out there and see if there is a minimum threshold and a maximum threshold to define a new range, which you know, basically is looking at any adverse effects and any sort of you know, detrimental reports that have been provided, because it seems like the evidence has been scanned by our panelists at least, and we don't have that specific percentage value for carbohydrates. And yes, it needs to be considered in the context with other macronutrients, but I think the range that was previously defined, as Alice pointed out, within the constraints that they had, you know, needs to be re-examined in the context of what is the minimum level below which there has been reports of adverse event failing a biomarker that is a clear indicator, which we've also recognized. And then, and likewise, what is the maximum sort of limit where there's clear harm or adverse effects that have been demonstrated.
Thank you. So that sounds like an AMDR, I mean, the minimum and maximum. No.
Yeah, now that we have also expanded the definition of the general population. So.
Right. Barbara?
I just don't know if you can do the minimum and the maximum that's going to be one size fits all. That's what worries me, is who is this minimum and maximum for? It really is very dependent on metabolic health. And, you know, and people don't know their own metabolic health, right? A lot of times people with prediabetes don't know they have it. So I don't know.
And that is a good point, Barbara. And I think there was a comment made that the chronic disease risk reduction component would be separated from it. And for that, of course, you know, there would be qualifiers, but in this other sort of group that we're calling the general population, that's about all that there seems to be by way of the evidence or the data that we have, and we've all been very made aware of the struggles and the constraints. So I agree with you. It's hard to do a one size fits all, and we're clearly moving away as a nutrition community to not do that. But unless we do, I don't know if you could do a repletion like study with cognitive and other fatigue kind of, documentation, having one value that would be the minimum that would need to be ingested in order to fulfill carbohydrate requirements seems to be a gap that we have on the table.
Christine?
Yeah, I just wanted to say in support of that, I mean, that's similar to the gestational weight gain guidelines that are separated out by BMI, right? Granted, BMI isn't the perfect indicator of metabolic health, but it's a relatively good approximation. And so I just wanted to support that statement that there's likely not a one size fits all, as there's not for reproduction with carbohydrate intake for women with obesity or overweight, and actually becoming pregnant. And it's likely different across all of those physiological stages.
All right, I see we've reached the end of the panel discussion time. At the risk of leaving out a lot of things, I'm going to just real briefly go through some of the highlights from the morning's conference here. So Dr. Beer made the point of humans can use ketones if they must or forced to for brain energy. Dr. Clearfield, you can design diets with low carbohydrates to meet fiber and micronutrient requirements, but it's not easy. And you have to rely on nuts and low starch diets. Dr. Gower provided a lot of examples of beneficial effects of low carbohydrate diets on metabolic health. And even in normal weight people, you may get some benefits there. She also importantly pointed out particular differences in ethnic groups, particularly African American women and Hispanics. Dr. Garner pointed out that perhaps we did not account for placental need for carbohydrates during pregnancy, and the issue of oligosaccharides, which do require energy to produce and carbohydrate, may not have been accounted for. And Dr. Lynch was asking a question about, where do we put oligosaccharides? Are they looped in with dietary fiber or not? The whole area of AMDR has been coming up, and plus it was a lot of the discussion recently. So we looking at AMDR, is there a minimum, maximum? Is it the right range? It's something that's less scientific, but required for labeling in the US at least, and probably for other federal programs. Also issue of the quality of the carbohydrate and the fat and protein should be considered, and we should consider quality of all the macronutrients. And then the question about biomarkers for a low carbohydrate diet really needs to be thought through, and it's a not easy topic. So I think in the end, we're not attacking an easy question. Otherwise, we wouldn't be having this webinar. And I think there's a lot for the parent committee here, standing committee to think about, but also the federal sponsors to think about as we try to move forward before either a large macronutrient panels put together or a carbohydrate panel put together. So I hope this has been discussion has been somewhat or a lot useful for the federal sponsors. I'm happy to give them a chance to respond a little bit. But I also want to remind everybody that this session has been recorded, and the recording and the presentation slides will be available on the project website in coming days. So happy to hear from Krista or Cindy if you have some final comments. Cindy?
I'll let Krista get the last word, but I just wanted to say thank you both to the standing committee and to all the speakers. The discussion today was exceedingly helpful as we decide how to go forward, and we really appreciate the time and thought that was put into this.
Thanks. Krista?
I'm not sure there's anything further to say. I think it really did cover our expectations in terms of looking at the different aspects that we need to consider. There's certainly a lot of considerations. I think you would agree. There's a lot of considerations going forward. And I think it's just given us real food for thought and information to consider. Thanks.
Thank you. So once again, I want to thank the speakers. I know you had to put a lot of time into your presentations, and this has been really interesting, and I've enjoyed all the discussion. Anything final from the Nutrition Board?
Just to add my thanks to everybody, from speakers to committee planners to staff. Couldn't have done this without everyone's collective help. So thank you very much.
All right, so thanks, to staff as well. It's gone very well. So this will be up on the website at some point in the near future. So those are people who weren't able to get on can see it. So thanks, everybody, and enjoy the rest of your day.
Great. Thanks, John.
Thank you.
Thank you, everybody.